I recently competed in a data science competition that put the data scientist in me to the test. I managed to pull off a surprising result with a pretty simple model, and I wanted to use this opportunity to kind of share some knowledge around the different kind of methods that I tried and different techniques that I used throughout this competition in a reasonable amount of detail. Hi folks, I'm Trent. I've been a professional data engineer for 6 years, and as mentioned, I want to take you through my solution for the IBM Skills Build Hydropower Climate Optimization Challenge. Still a mouthful. And what I want to do is walk you through my solution code and kind of all the attempts that I made throughout. I also reached out to the winner of this competition, so spoilers, I didn't win, but I reached out to them and they said it was cool if I walked through their solution or just touched on their solution at a high level. I really think this is a valuable way to share some knowledge on this type of problem, kind of show you the messiness involved with one of these competitions, and hopefully help you along your journey. Now, throughout, I will leave links in the description, like chapter by chapter, for different topics that I think are advanced topics. So we will be going through some stuff that is a little more advanced than I usually go through. So I'll leave some links to content that I think is relevant and places where I feel that I don't flesh out the concepts enough. So keep an eye out for those. I'll also, of course, leave a link to the repository that we're going to walk through as well if you want to follow along at home. All right, so for this challenge, or going through this challenge, which ran in April of this year, I just wanted to take you through the context of it. The idea was to predict power production from micro-hydro power plants in Kalam in Pakistan. The idea is to use the kind of power production data given to you in the competition to forecast 31 days into the future. You could use the initial data, the power production data itself, and they provided climate data as well, because of course with kind of hydropower, climate affects this. So things like rainfall and water levels in rivers and that kind of stuff is going to affect how much power is produced. So that's all given to you as part of the competition. But as I say, the main objective here is to produce the best forecast you can for 31 days into the future. And the idea is that you will produce a forecast in a CSV format. So if I jump over to this data tab, and we'll go through these in a bit more detail or use these, there is a sample submission over here that shows you the structure of the submission expected. And basically you'd produce one of these files based on a forecasting model. Go ahead and click on get a score. You can drag and drop your forecast over here, and then you would get a score. Now, the scoring used is for the root mean square error of your forecast. So they know the true data that you're forecasting for, and they kind of compare your forecast to that and produce a root mean square error. So the lower your error, the better your score, basically. Now, jumping back to the data tab, there is the data that you can use for this competition. So part of the rules were that you could only use the data provided. You can't use external data. Some competitions do allow you to kind of pull your own data if you have it. But in this case, you were only allowed to use the data provided. So there's two data sets, or two main data sets provided. That is the data over here, which is the hydropower production data. So we'll go through that in a little bit. And then the climate data over here, which provides you the different kind of climate statistics like rainfall, snowfall, these kinds of things. We'll go through these in a bit more detail. I just wanted to show you where you can find these. Now, also as part of these competitions, there's typically a starter notebook provided. Now, these are really handy for different types of data science competitions because often they kind of give you an end-to-end flow of how to process the data, or like a basic model processing the data, and importantly, show you how to create a submission for these types of competitions. So it's really useful to go through one of these, and we'll actually go through the starter notebook together just to get an understanding of how the competition works and kind of the system that we're operating in, right? So get the picture of what we're doing a bit clearer in our minds. So let me jump over to my editor for that. Okay, jumping over to the editor, I have got a virtual environment set up. I'm using Python 3.10. So if you want to match exactly what I'm doing, I'd recommend using Python 3.10. And if you want to get all the requirements that I'm using, so all the different packages and stuff, I've left a requirements.txt file here. So you can just go ahead and pip install -r requirements.txt, and this will install all the packages that I'm going to be using throughout and the exact versions that I'm using throughout. So pretty handy. All right, I'm not going to run that because I've already got everything installed. Okay, so let's go ahead and open up the starter notebook. So over here, I'm just noting that this is the starter notebook provided by Zindi, the competition website. The original can be found here. This is just a link to it, along with any data used for the challenge. It can also be found there, that exact tab that I was showing earlier. I just wanted to note this because this isn't my work. This is the starter notebook itself. All right, as any good notebook starts, we've got a whole bunch of imports. Now, already it seems like we've got some unused imports, which is interesting, but you know, I'm not going to modify or change that. I am just going to go ahead and run this. So we want to import pandas, numpy, matplotlib, and then also the stats models packages over here, as well as, it looks like this sklearn metrics over here is not actually being used, but hey, I'll import it anyway. Cool. All right, let's let that run. All right, with the imports out of the way, we now go ahead and read our data into data frames in pandas. So over here, we've got all data df, which is reading the hydropower production data, and then ss over here, which is reading the sample submission. So I've gone ahead and downloaded the data from the competition website already. I've put it in this data folder over here. So I've downloaded and unzipped the data, and I'm then just pointing to this directory over here. All right, so let us go ahead and read in our data. Now, this is going to take a while, and we'll explain why that is in a minute. So let's let that read in. Okay, a whole minute later, we have got our data in data frame. So let's take a look at all data df, and this will hopefully explain why it took so long to run it. So if we take a look at a high level, this dataset has like 39 million different entries. So this is a pretty big boy, right? This is quite a lot of data to deal with. And that explains why the data takes so long to read in. Now, the immediate reaction that you may have is, okay, if we're dealing with such big data, should we like jump to using like Apache Spark or Polars or that kind of thing? Those are viable solutions, but I'll take you through how I dealt with this in a bit. This was like my first gut instinct, but I came up with a solution that I think is just as efficient and a bit simpler than using any other packages. So we'll go through that. Okay, scanning through this, let's take a look at our data. At a high level, we have these different columns, and we'll take a look at these in a minute. Another thing to note is that this is using about 3 gigabytes of memory. So with pandas, basically your data is read into active memory, or RAM, should I say, like roughly 3 gigs of RAM, which is a lot, right? So I have a pretty powerful machine, not to brag or anything, but so I'm okay. But I think that we need to deal with this kind of problem because not everyone has a powerful machine. So we need to kind of tackle this, and we're never sure of like how powerful a server this is going to end up running on. So we need to take this into consideration. Anyway, let's take a look at the first few records of our data by doing a .head over here. And it looks like we get a date time, and these are in 5-minute intervals. So you can see that we get a date stamp and a timestamp, and this looks like every 5 minutes we're getting a recording. We have V red over here, which I think is a voltage red, the amount of current, a power factor, and the kilowatt hours. So this is our target column over here. How many kilowatt hours of power is being generated? Then interestingly, we have the source column, which expresses a consumer device and a data user. So we've got consumer device 10 and data user 1. Now, when we look at the data in a bit more detail, we'll see that there are many consumer devices and many data users as well. So this isn't a single time series that we're forecasting for. It is many time series that we are forecasting for, but we'll visualize that in a bit. Then we've got voltage blue and voltage yellow. These are missing values. And then there is this consumer device 9 and consumer device X column. I think this might be an error in the data itself, but yeah, basically I ignore these. Going through the competition, I just kind of assumed that these were errors and basically filtered them out as soon as I could and got rid of them. So yeah, just something to note there. So hey man, real data, real problems. All right. As I mentioned, it would be interesting to see how many unique sources we have. So let's take a length on all data of the source column and take the unique values. So how many unique values does source contain? And this turns out to be 585. So quite a lot of different series that we're dealing with, or 585 distinct time series that we're dealing with. Now, if you remember, we also read in the sample submission, and the reason I did this was because I wanted to take a look at, are we forecasting for the full set of sample submissions, or are we forecasting for a subset of sample submissions? So yeah, sorry, these couple of lines I did add into the sample notebook just as high level analysis, but the majority of this notebook is pretty much what you'd get with the starter notebook. So I just added this in to take a look, basically see what the format looks like, and then acknowledging that this sample submission has an ID column, and the ID column is comprised of the date stamp and then the source stamp as well, separated by an underscore over here. So that's how the ID is calculated, and then it gives you a kilowatt hour forecast, or you need to produce a kilowatt hour forecast for these dates for these different device user combinations. Now, in the case of the sample submission, it's just a bunch of zeros, so this is not good, right? As a submission, it's just kind of giving you the IDs that you need a forecast for. To deal with this, I actually want to get the sources alone to like get the unique sources that I'm actually dealing with. I basically want to split this value by the underscore over here and split that up into two columns, the date and the consumer device, or sorry, the source column. And that's exactly what I'm doing here. So taking the date and source, and then using string.split on this this character over here, saying to expand it into multiple columns, or expand the results into multiple columns, and then saying that I only want to do the split at n equals 1. So the very first time that it sees one of these splits, go ahead and do it, and then split up the columns. That's what this n equals 1 means. It's basically, if I'd specified anything else, or like a higher number, it would also split these other underscores as well. All right. Then I take a count of the unique different sources in the sample submission, and it turns out to be 194. All right, so we've got to forecast for 194 out of the 585 total series over here. All right, so this is jumping away from my code and now into the sample submission code itself. So this step over here splits the source column into consumer device and data user over here. So let's go ahead and take a look at this. Okay, after a minute and a half, we eventually get our result. So man, yeah, this data size is already getting to us. But basically this just splits up that source column into a consumer device column and a data user column using regex over here, or like a regex pattern. So it's using string.extract to achieve that. All right, then there is this list of devices to drop. So this is specified as devices that are not in the sample submission, which is interesting. Another piece that I kind of read on the competition forum or noticed as part of the discussions is that these devices have very weak signal in them. So they weren't very easy to forecast for, or not worthy of being forecasted. So this was noted in the sample submission and nowhere else. So interesting one, but yeah, basically this just puts together a set of different consumer devices that are not in the sample submission and basically have weak signals. Now, this section over here of the sample submission was a little confusing to me because it does a filter over here. So it creates filter df. And the way it does this is basically looks at all data consumer device is in this devices to drop list, and then produces the filter df.head. So we get to take a look at them, but the thing is, this filter df isn't used again in the sample submission, which is kind of strange, but hey man, I thought I'd mention it. But yeah, if you want to look at what these, this data looks like, you have filter df, but just a note, it's not used again in this notebook. So is what it is, I guess. Anyway, moving on. The next piece over here is aggregating the data. So something that I didn't note and should have noted is that in the sample submission, the dates, so where did I put this guy? Oh, yeah, here, over here. The forecast timestamps are basically at a daily level. Now, if you remember, our actual data is at 5-minute intervals, yet the forecast is at a daily level, right? So there's different time granularities in the data. Now, to deal with that, the sample submission notebook, or yeah, the starter notebook, should I say, it goes ahead and produces an aggregate of the data. So what it's doing over here is extracting the date part of the date timestamp by using this .dt.date over here, and then aggregates per source per date the kilowatt hours and uses a sum on that. So what we're really forecasting for is not these 5-minute intervals, but rather a daily sum of kilowatt hours produced per source. So a bit of a distinction there, and an important distinction to note that the granularity we are forecasting at is daily and not at 5-minute intervals. So this is why this aggregate is being done. So let's go ahead and execute this guy. All right, and from the output, we now get a source per date kilowatt hour sum, basically, in this aggregate. So we now have the sum total kilowatt hours produced for a particular date for a particular source, and this is what we want to forecast for. So in the starter notebook, we now can visualize, or it visualizes the data for one of the devices, and this is a consumer device 10 over here. So it's kind of arbitrarily picking this device to visualize. It basically plots out the signals for all the different sources. So remember, these are consumer device user combinations. So all of the different users of consumer device 10 will get plotted in this code. So let's go ahead and run this guy and see what the data looks like. And already the amount of time series becomes overwhelming, right? There is a whole bunch of different users for this one device, and we are dealing with multiple devices. So this already gives you an idea of kind of how overwhelming this problem can become. But nonetheless, we persist on. And in this plot, we notice that there is these kind of spikes in power over time. And it looks like this data ranges from July 2024 all the way up to September 2024. And in between, there's like spikes in power, basically in power production. And then there's periods where there's no power being produced. So that's interesting, right? There's like no power over here, and then like a little spike, and then a whole bunch of power getting produced after a period of like almost no power being produced. So this plot basically gives us an idea of what the data looks like. Of course, it is just a subset of the data, but nonetheless, this is pretty useful to see what the power production data looks like. Now, in the next step of the starter notebook, the minimum and maximum date is found across the aggregated data. So here we notice that this is from July 2024 up to September 2024. But let's take a look and see if the dates align, basically, or the minimum and maximum dates align across all the different time series. So running that, we immediately notice that actually one of the earliest dates is June 2023. So the next complexity is that the time series are different lengths, right? So each of the sources have different lengths of time associated with them. So you may have an instance where a device was active all the way back in June 2023, all the way up to September 2024, or maybe a device that was active for a period in between here and not active like towards the end of the data. So you've got these different ranges to worry about. This next block of code in the notebook basically will deal with this problem of having multiple length time series by extending the date range such that all the time series are the exact same length. Now, what do you do when you have a circumstance like this, where you have data from July 2024 and the earliest date is actually June 2023? It'll basically extend the data set and then fill the missing values, or all the values missing prior to this, with a 0. So just walking through this code at a pretty high level, you create a date range over here, or a date range gets created. Let me get rid of this IntelliSense. Annoying. Anyway, so a date range is created between the min and max date, and then a new data frame is spawned over here, an empty data frame. And then in this for loop, what is done is each of the sources, so each of these different time series are taken and conformed into this extended time frame, right? So we take each individual source, so for each of the sources in the aggregated data, so these different unique sources over here, we have a for loop that runs through each of them, and basically the main operation is this merge step where we merge the selected time series with the full date range, and then go ahead and fill the NA values, the missing values, with the 0. Then right at the end over here, the step taken in the for loop is to concatenate all of the data together into one big data frame. Into this empty data frame then gets populated basically with each of the extended time series. So we now end up with a complete data over here. This data frame is all of the time series, and they are guaranteed to have the exact same date range per series. All right, so let's go ahead and actually run this guy. I almost forgot to run this. And taking a .head of the complete data, we have the same setup as before, but now the date range is much longer for some of these time series. So for consumer device 10, it now extends all the way back to 2023, but there's a whole bunch of zeros populated in here. All right, let's get to the fun part, right? Over here, there is a function put together that creates a forecast using ARIMA, and I'll touch on that in a few. But basically, in this function over here, we accept all data, a forecast horizon. So how many time steps in the future do we want to forecast for? Over here, they've set a default of 30. Now, interestingly, in the actual competition and in the sample submission, it's actually 31 days. So I think this might be a typo. But, nonetheless, this is the default value of 30 days. And there's this output template over here, which is basically used to conform your forecasts into the sample submission kind of state, like that the setup that the sample submissions have. This is used as an argument to kind of specify that. So just walking through this function, we take the all data frame that's passed to it, convert the date column that it assumes it has, and convert that to a date time type. We then extract the consumer device and data user over here using a very similar technique as we had like in the beginning. We sort the values of the data by consumer device, data user, and then date, all in the default ascending order, and then set up a list to contain all the different forecasts. So the idea here is that each forecast is going to be a data frame. This is going to be a list of each of the data frames. So for every single device user combination, this is going to go ahead and forecast for it. All right, and then we have a fun for loop over here that's going to go through every consumer device and data user combination over here. And we'll basically do this kind of like a setting of the index of the data frame as the date column. This is needed, I believe, for the forecasting model that they use, which turns out to be the stats forecast ARIMA model. So you need your index of the data frame that you're using to be the date. This also uses a forward fill over here. So this fills NA values with a forward fill. Now this is interesting because the pre-processing steps actually fill all the null values already with a 0. So this feels a little weird, but hey, that's just how it is, I suppose, in this notebook. So if you did have null values in the all data provided in the function over here, this would then get filled with the forward fill method if there were null values. But, like I said, all the null values have been filled with zeros already. So a little strange there. And then it goes ahead and tries to fit an ARIMA model to this. So it uses a try except block over here. And if it fails, it's not going to break the for loop. Basically, if any error happens in this block of code, it'll jump to this exception block over here and say, hey, there was an error processing this consumer device user combination. Okay, now to go through this forecasting code, a model is set up, and this is stats forecast ARIMA over here. And ARIMA is the auto-regressive integrated moving average model. Now, this is one of those topics that I don't think I can treat in sufficient depth in this video, but I'll give it a shot nonetheless. I will leave a link in the description to another creator's video, a creator called Ego Howell. I actually used their video to review ARIMA because I hadn't done this in a really long time. So I watched their video and I thought it was really good. But just to give you a quick high level and break down what ARIMA means, the autoregressive part is pretty typical in time series. Effectively, you have a regression model like this, like y of t equals some constant, and then a coefficient times And over here, you're not using traditional predictors. This is what makes time series forecasting interesting, or autoregression interesting. You're actually using previous values of your target. So if we're trying to predict kilowatt hours today, we could use yesterday's value, or the day before's value, or the day before that's value. And autoregression will use a number of these terms in the past as features. So this is what makes time series a little different to kind of like traditional machine learning, in that you can use these autoregressive features, which is basically your target variable in the past is used as a feature for today. Hopefully that makes sense. But yeah, effectively this is the autoregressive part. You use a regression model on top of your target variable itself. The integrated part of ARIMA, or the I in ARIMA, refers to the amount of differencing that you apply to the series. So in time series forecasting, a technique that's often used is this differencing, which basically means instead of me predicting, in our case, kilowatt hours, I'll predict the difference between yesterday's value and today's value. Or, throughout basically have differences, and I'm predicting differences as opposed to the value itself. Now, this helps achieve stationarity. Stationarity is a bit technical, but it's a nice property to have in time series forecasting. Again, I'll leave a link to a video on stationarity that I found useful to review this concept. And then lastly, the moving average component of ARIMA over here. Basically, you're using your past forecast errors instead of the actual observed errors in your model. So now you are using these terms, linear terms, of how far your forecasts deviate from the actual value in the past, right, with coefficients. And again, I'm treating this at a super high level, but basically ARIMA's final form is taking this autoregressive component, the moving average component, and you optionally can apply differencing on top of your data. So instead of y, I'm using y prime here to represent like if you're forecasting a differenced value rather than the value itself. All right. Hopefully I did not botch that too much, but I just wanted to give a brief overview of the ARIMA model. It's one of these pretty typical time series forecasting type models. In this case, it is forecasting kilowatt hours, right? That's our target variable. And this order represents the different parameters for each of those components. So what I mean by that is, in this case, this 5 represents the autoregressive or AR part of ARIMA. So this is using 5 terms or up to 5 terms in the past as part of the autoregression. It is applying a differencing of 1, which means it differences the dates or the values once. And it's actually not using moving averages because this is 0. So basically all the coefficients will be set to 0. So this is more of an ARI model than an ARIMA model. All right, with that in mind, we call model.fit. So pretty typical kind of stuff in the ML world, model.fit on top of our data, and then perform a forecast on a specific date range. And this is created according to our forecast horizon. How far in the future do we want to forecast for? Then the results are stored in a particular format, or in the format that we want them. So this uses a kind of format string over here to say, hey, go ahead and take the date for each of these. So take the date stamp and then put the consumer device and data user in the ID column, and then use the forecast values as the kilowatt hours here. So this creates a dictionary first, and then that dictionary is used as an argument in the data frame. Oops. There we go. This is used as an argument in the pd.dataframe method over here. And this creates a forecast data frame, and this gets appended to that list that was instantiated all the way in the beginning. So this goes through each and every source, creates a forecast using this ARIMA model, and will append it to this list of forecast data frames that we have. All right, then this last step over here combines all the forecasts in that list into a single data frame. And then if there is an output template provided, this looks like it's trying to align. Yeah, this part confused me a little bit because there's already formatting being done over here by default. And then this is, what is this doing? Oh, okay, this is joining with the sample submission or the output template if you give it to it so that you're getting the exact forecasts. Okay, so this is just limiting if you forecast for more series than are in the sample submission. This is making sure that it drops all of those additional forecasts. I don't really like this, to be honest. But hey, that's just my opinion, and who am I to judge? So I wouldn't do something like this. This is a bit strange, but hey. Uh, anyway, moving on from that, the output template is used to kind of limit your forecast, and then we return this one big data frame. Okay, so this was going through a function, so let's actually run this so that we have this function in memory. And we go ahead and call this function on our data with a forecast horizon, again, of 30, which I think is a mistake. Again, it should be 31. I'm going to go with it. And this uses the output template of the sample submission data frame. So if I go ahead and run this, this will actually go and loop through all of the different sources, produce a forecast using the ARIMA model. Okay, so after letting the forecast run for about 2 minutes almost, takes a little bit of time, taking the forecast and taking a look at this full data frame that we have, which contains all of our forecasts. So the big data frame looks like this. We have our ID, date, and source, and then the kilowatt hour forecasts for days into the future, basically. All right, and interestingly, if I scroll down, some of these comments in the starter notebook have prompt in here. So I don't know if this is from like a AI assistant or something like that, but hey, you know, I just thought it was interesting. Is this the future of programming? We just have in our comments the prompt we used. Anyway, nonetheless, this goes ahead and fills NA values again in your forecast, which I don't like this at all because this means if you skipped a forecast or something, it's like, just make it 0, which I'm not such a big fan of, but hey, you know, we'll run it nonetheless. Then look at the length of the complete data, the forecast, and the length of the sample submission, just to compare them. So this had 280,000 records. The forecast has 6,014, and the sample submission has 6,014. So it looks like we are good in terms of length. Then we just want the ID in kilowatt hours from our forecast data frame up here. And I'm going to save this to a location on my local machine called submissions, the submissions folder. And I'm just going to call this starter notebook forecast.csv and not include the index over here. So under submissions, this is empty right now. Yeah. All right. So let's just run this and generate a submission. All right. So that gives us our CSV file. And there we go. We have our ID and the kilowatt hour forecast for that particular ID. And then down here, there is some more code. This is just to check the difference between the forecast and sample submission. If there is any difference, it just basically uses a set difference to compare the IDs to make sure that all the IDs that you actually need are in your forecast. This is really being overzealous about checking. You know, I appreciate that, so that's fine. And yeah, there's no difference between the sample submission IDs and the forecast IDs, so that is good. Okay, so just to illustrate to you how to use one of these forecasts. So we've gone through this whole process of pre-processing our data, putting it through an ARIMA model and producing a forecast. Now to actually get a submission, which you can still do. Even though the competition is over, you can still go ahead, take a forecast and get a score for it. So I'm going to go ahead and just show you what that looks like. So jumping over to the site over here, I can click on get a score and then drag and drop my submission in here. All right, there we go. Dropping our submission in, we can click on get a score. This has all my scores from all my attempts. All right, and there we go. We get a public score. So this is like the scores you'd get before the full data set was revealed in the competition. So they kind of test you on a small subset of the data and then right at the end actually unveil the full data set in these types of competitions. So our public score is a root mean square error of 8.41. And the private score is a little better. It's 6.44. And so if this is a root mean square error, so it's in the units of the forecasted variable. So this means like on average, we're off about 8.4 kilowatts, but in total, we're actually off by about 6.4 kilowatt hours. So that is the process of one of these challenges. You basically go through your data processing, create a forecaster, create a forecast submission, and then basically drop it in the submission section over here and get a score based on the data that the competition knows, like the true data or the real data. All right, that concludes our kind of first step over here, which is just to going through the starter notebook, understanding how the competition works, the basic process, the basic components of the data that we're dealing with, what it looks like, and all that kind of thing. And now I will move on to kind of my code and how I tackled this problem. Now, I do have an appointment in a few minutes, so I'm probably going to pause recording here and return to this, so I might appear in different clothes. All right, I'm back and ready to continue. So the next piece that I want to go through is my data preparation, and really the focus here was to deal with this kind of large data set of the kilowatt hour power production, so the kilowatt hour power produced data set, dealing with this large data set and getting it down into an aggregated form. So again, we are forecasting in the granularity of days, and the data is actually represented or given to us in the granularity of 5-minute intervals in the case of the kilowatt hour data set or the power production data set, and in the intervals of 1 hour for the climate data set. Now, we haven't gone through that yet, but you'll see what I mean when we actually touch on the climate data. It also has a different granularity. So the goal is to get the data into daily granularities. This makes sense from what we want to do, our forecasting objective, right, which is in the granularity of days. All right, let's jump into the data preparation step. So opening up this notebook in the repo called datapreparation.ipynb. And let's just close the starter notebook. Let me jump to the top over here. Now, the main objective here, or one of the main objectives at least, that I wanted to show off in this notebook was dealing with the big data set. And because of this huge amount of data in data.csv, or reasonably big amount of data in data.csv, I used DuckDB to process the data and kind of handle it. Now, the reason I do that is because DuckDB, if you're unfamiliar with it, is kind of a local database, or you can use it as a local database. It's kind of like SQLite, if you've ever used that before. You effectively can store data on disk rather than in RAM. So pandas will store data in RAM and keep it active and kind of use up your RAM. And if data is just hanging around, your RAM can fill up pretty quickly depending on how much RAM you have available on your machine. And with DuckDB, it stores it on hard disk, right? It acts as a database. It is a database. And it's super efficient at dealing with OLAP type data. And by OLAP, I mean online analytical processing. So dealing with these large volumes of data and being able to aggregate those and perform different operations on top of them. So DuckDB is really powerful. I've used it in previous videos. I'll also leave a link to an article on DuckDB. I think it's such a cool tool, and we'll take a quick tour of it by doing this activity over here. Okay, so first things first, let's actually import pandas and DuckDB. So we're going to be using the DuckDB Python API over here, and that's as simple as, import DuckDB, and I like to alias it as DDB. Let's go ahead and run this guy. All right, with the imports done, the steps, or more specific steps that I'm going to take, is actually creating a DuckDB instance. I should actually say instance of a database, because we're going to be creating a database. And then importing the data from data.csv, the climate data, which happens to be in an Excel spreadsheet. So unzipping the data, you'll see an Excel spreadsheet with the column climate data in it. And taking that as well as the sample submission data, because we use that pretty frequently to check our forecast sample submissions, or sorry, our forecast submissions themselves. So I want to import all of those into my database, then aggregate them into daily granularities, and then use the database as and when needed to store data. Basically, we're going to use it as a database, right? A place where we store our data, and we can call it and use it wherever we need it. And DuckDB makes this super convenient. The Python API makes it super convenient, and you'll actually see that play out. All right. So to create a database using the Python API for DuckDB, it's as simple as calling duckdb.connect and then giving your database a path and a name. So this is going to create a file, or a .db file, which represents our actual database in our repository over here. So this is going to create a database called column_hydropower. And this connection instance over here, or this object, will let us access that database and operate on top of it from our Jupyter notebook in this case, but you could use this in a script wherever you want to. And yeah, this is the process we're going to go through. First, create the database. Then I use this connection to execute two SQL statements. The first creates a schema called raw. The second creates a schema called prepared. So I'm following the patterning idea of like a typical data engineering type workflow, where I have a raw schema where I capture all my data, and a prepared schema where I'm going to put more kind of like data that I've operated on. So when I say data engineering workflow, this is pretty typical of ELT jobs or extract, load, transform jobs. It's like capture all your data in its raw state or as raw as you can get it, and then take the data and prepare it, like you manipulate it into a easier to work with form. So these two schemas represent that separation in the data. I'm going to go ahead, create my database and connect to it, and then try and create schemas. Now, if those schemas already exist, this will throw an error saying that, hey, you're trying to create a schema, but that schema already exists, or a schema with that name already exists. And it will throw an error out and kind of stop your notebook. So I've just wrapped this in a try except block so that if the schemas already exist, I get this DuckDB catalog exception and I print out a message saying, hey, the schemas already exist. In case you want to run this notebook multiple times, it doesn't stop the flow of the notebook. Whereas if an error was thrown and this try except block wasn't here, if you ran this twice, it would get stuck at this point and you'd have this nasty error message appearing. So these try except blocks are simply for that purpose, just to keep the flow of the notebook or flow of the script good. With that said, I am just going to go ahead and run this block. And there we go. We have got our hydropower database or column hydropower.db file created. And this was successful, so it should have created two schemas for us, raw and prepared. Now, you'll notice there's also this db.well file. And what this is a lock. So with DuckDB, you can have many readers, many concurrent readers on the database, but it only allows one writer. And in our case, we're connecting to it such that we are able to write to the database, not just read. So if I had an argument over here of read only equals true, that would mean that I was just putting this in read only mode. And that would be fine. I wouldn't need to acquire a lock for that. But since I'm doing writing, this lock prevents me from having multiple writers operate on the data at the database at the same time. So just to point that out, once you close the connection or close your writer connection, this .well file will disappear. All right, with that being said, the step that I'm going to take over here is to select the top 10 records from our hydropower data. Now, DuckDB, again, like I always nerd out over it because of how impressive it is, but I can write a con.sql over here. So I'm taking our connection object, calling the .sql method, and then entering in a SQL string. And in the SQL string, I'm selecting star, so select all from, and then I can read a CSV directly in DuckDB. And then call the top 10 records. But the impressive part is this read CSV function over here. I can read my CSV directly and it will print out the data for me. So I find that quite cool because data of different formats can be read using DuckDB and it will just print out the results for you. And then we're actually going to use this to copy the data from CSV into DuckDB directly. So we don't have to do any kind of like weird tricks where we have to load it using a specific connector or anything. It has built-in functions for a ton of different file formats. And in this case, we're going to use CSV. And later on, we'll use Excel. Actually, you can read an Excel file directly into DuckDB and create a table from that, or manipulate the data using DuckDB. So yeah, sorry if I nerd out a lot, but I find this quite cool. So let's run this. And this will show you that you get your top 10 records. And something else impressive that it does is that it auto casts data types for you. Now, these are not necessarily the best all the time. It's going to use a sample of your data to infer what data type to use. But in this case, for datetime, it's picked up that it is a timestamp type. It is a date and a time at the same time. That was a weird sentence, but you know what I mean. This data type is correct. Then for our voltage type, it's a double, which is correct. Current is double, power factor is double, kilowatt hours is double. And if we scroll to the side over here, the source is a varchar. Now, the one thing it has gotten wrong is that voltage blue and voltage yellow are picked up as varchars. And I suspect this is because there are a ton of nulls. So it's basically taken the top X number of records and try to infer the type. It has seen a ton of nulls. It's not sure what type to cast it as, so it defaults to a varchar. So we'll need to explicitly cast these to doubles. We expect these to be double types, much like voltage red is. And then these last two columns, again, I think these are mistakes, so I'm basically going to ignore them. All right, noting that, we can move on to using read CSV again in DuckDB and create a table. So I want to create a table in raw that represents my hydropower production. So basically taking this data.csv, all of the data, and dumping it into a table in DuckDB. And again, I'm just following this try except pattern to not interrupt the flow if we ran this twice, because if we try to create a table with the same name twice, we would get an error or a catalog exception. So I'm just handling this gracefully, let's say. Cool. So in this case, the statement that I'm using is a create table statement. Then I'm specifying the raw schema, giving the table a name, hydropower production as, and then I select the columns that I want explicitly because I want to ignore those last two columns. So I'm going to do an explicit select. And generally this is best practice. You specify the data that you want from your source. So over here, I select date time, and then source over here, or the source column, I'm going to rename it to lowercase source. Now, this is me being a bit pedantic because I like snake case and we're working in Python, so it's pretty typical to use snake case. I don't want to have capitalized names for my columns, so I'm going to make this look a little nicer and call it source. So I alias the column. Then I select voltage red, and then I cast voltage blue as a double as well as voltage yellow as a double. So I'm doing that cast so they're not picked up as varchars, they are picked up as double. All right, and then just selecting current and kilowatt hours and ignoring these two columns that I think are errors. All right, so doing that explicit select and using read CSV to read everything, we're going to go ahead and execute this and get all of our data into our DuckDB database. So let's go ahead and run that. All right, and in 12 seconds, we get all 39 million records into our database file over here. Okay, then the next step is I want to actually extract the climate data over here. And in this case, I need to read Excel. So in DuckDB, I want to use a package, an Excel package. And to use that or use a package, you need to install it for your DuckDB instance, right? So I'm installing Excel and then loading it so that I can use this read Excel, or I can use this kind of syntax where I just pass it an Excel file and it knows what to do with it, right? So in this case, I'm just reading the top 10 records. So let's go ahead and run this guy. All right, and we can see our climate data appearing over here. And as I alluded to earlier, the intervals for the climate data is at an hourly granularity. So every hour, these different statistics are recorded. And just taking a look at it, we get factors like temperature in degrees Celsius, dew point temperature in degrees Celsius, the different wind components, oops, extra block there, different wind components over here, the total precipitation in millimeters, the snowfall in millimeters, and the snow cover percentage. All right, so this is pretty useful data to have, right? This helps us judge the climate in the region. And so I'm going to load this into raw. The one thing to note is that the column names have these kind of weird symbols in them, like degrees Celsius and such. To make my life easier, I'm just going to cast these so that when I call this data or use this data, I don't have to care about having these weird characters and that kind of thing. I'm just going to keep it in snake case and make things easier for me to type out. So I'm going to change these names or alias these names to what I want. Otherwise, the data types all look correct. These are all doubles, and the date space time over here is a timestamp. So I'm happy with that. All right, and same process as we did with the data, data.csv. I'm going to create a table called climate in the raw schema. I'm going to select each of the columns and just give them more appropriate names. So date space time, I want to call that date underscore time. Temperature, I want to call that temperature all lowercase, or temperature degrees Celsius. I'm just going to call that lowercase temperature. And similar idea with the rest of the columns over here, just renaming them so that it's easier for me to use this data. Alrighty, and again, we can just say from this file over here, and it will automatically load in all the data. All right, and that was super fast. We got all the data for the region, all the climate data, and it's all loaded in and exists as a table called climate in the raw schema. All right, and just to check that our data looks appropriate, let's now select star from our newly created table and just look at the top 10 records. So running that, we have got these columns that have nicer names, in my opinion, and it looks like it has gotten the data correctly. All right, the next thing is to go through the exact same process, but with the sample submission CSV file. In this case, I'm just using the read CSV function. So going to create a table called sample submission in the raw schema, just reading all the data from the sample submission. So running that super quick because this file is very small. And then just to inspect the data, let's take a look at the top 10 records. Yeah, that looks good. IDs of varchar, kilowatt hours. This is picking it up as an int64. I don't worry about that too much. It's just because these are all zeros. I'm okay with that for now. Okay, with all of our data loaded into the raw layer, now we can move on to actually manipulating the data and effectively just aggregating the data such that it is at the right granularity. So the climate and the hydropower production data are both at the daily level rather than at the hourly or the 5-minutely level. I just want to get them to daily. All right, I explained that in my notes over here. But to move on to the first aggregate, I'm going to aggregate the power production data, so our kilowatt hours data. And over here, I'm going to create a new table called prepared daily hydropower production. And I'm going to use a CTE over here, and that's a common table expression. And I'll explain why I'm doing that in a minute. But the first thing I'm going to do is create a temporary table called temp for temporary. And so with temp as, I select all the columns. I then cast the date time to a date. So I'm creating a new column called date. Should maybe choose a more or less confusing name than that, but we'll go with it. So this is a column called date, which represents just the date part of the date time stamp. So no hours, minutes, and seconds, just the date part. Then I'm using the .db function regex pattern extract or regexp extract. And I'm going to do this on the source over here. And I want to extract the consumer device number. So that's what I'm representing over here. I'm using a regex group over here to say, hey, when you find the pattern consumer underscore device, then you see some digits over here or digits repeating. I want you to extract that as the consumer device over here. And similarly with the data user, I just want to extract the data user number as well. So I've created these three columns, date, consumer device, and data user from our raw table, raw hydropower production over here. So that is our temporary table over here, or our common table expression. I then, to actually create our physical table, I do another select and I just select date, source, the new columns that I created, consumer device and data user. Date is also a column that we created. And then the sum of kilowatt hours over here as kWh. So I'm just aliasing the sum as kilowatt hours at this daily granularity from our common table expression or temporary table. I'm grouping by the date, source, consumer device, and data user. So I'm taking the sum across all of those different columns and then ordering by the source and dates just to make the data look a little nicer for the ordering to also make sense. Now, the reason I used a CTE for this is because of these operations over here. Now, in SQL, if I were to do this all in one statement, and I would need to have these operations in the select statement over here, but then I would need to repeat these operations in my group by. I need to specify date, consumer device, and data user. But if I were to do this all in one go, I would need to have these statements, the regex pattern extract and the cast, all happening over here as well. So I'd effectively need to have these long statements twice. And the reason I'm not doing that is just for readability. And the reason you have to do that is because of the way that SQL is evaluated. You can't create an alias in your select statement and then use that alias in like a subclause like a group by. So this is just purely for readability. You could do all of this in one statement. It just doesn't look as nice, in my opinion, at least. So it's just me being pedantic, really. But I think this is a bit more readable. All right, let's go ahead and create our aggregate table. All right, again, pretty fast, 4.6 seconds, and it has aggregated all 39 million plus records into the daily granularity rather than 5-minute intervals. All right, and I want to go through a similar process on climate. Before that, I'm just going to inspect the data to make sure it looks right. So let's take the top 10 records from our newly created daily hydropower production table. And this looks pretty good. We've got our date over here, so no longer has timestamps. We've got our source over here, which tells us the device and data user. And then we've got the numbers actually split out here, the consumer device and the data user over there. And then our kilowatt hours. Now for this, I've not included the other features of the kind of voltage, the current, the power factor. And the reason is because of kind of hindsight. I don't end up using those columns. They might be useful. I just didn't include them in my analysis. I tried using them and I wasn't really getting good results with them. They weren't correlating well. They didn't really tell me much. And I couldn't figure out a nice way to actually use those features. Maybe you can figure out a good way to use current and power factor and voltage and all that good stuff. But I didn't end up using them, so I just kind of rejected them from my prepared table over here. And that's my reasoning why I did that. All right, then moving on, I'm going to do the exact same kind of aggregate move with the climate data. And in this case, I'm just grouping by the date. And this is a good example of me using the kind of like cost statement here and using it in my group by. So I am doing this all in one statement. I just thought that this, because I'm doing a group by with one column, this made more sense. This was pretty readable in my opinion. If I needed to do a move like we were doing with the hydropower production data, I would go ahead and, use the kind of common table expression type of pattern. But in this case, this is reasonably simple. So I just turn the date time into a date. And now I need to think about these statistics that I'm going to use for aggregation. And in my opinion, what made the most sense was taking the average of the temperatures, so the dew point temperature and just normal temperature over here, then taking the average of the different wind components, taking the sum of the total precipitation. This made sense to me intuitively, and then the sum of the snowfall as well, and then taking the average of the snow cover percentage. So I'm taking all of these from my raw climate table over here and performing these aggregates on top of all of the columns and then grouping by the date to turn this into a daily granularity data asset or table. And this just makes things a lot easier. I no longer have to care that it's at hourly increments. It is now at daily increments. So let's go ahead and execute this guy. Again, pretty fast to do that. This data isn't as big as the hydropower production data. All right, and then let's just inspect this guy. And yeah, this looks good. We have achieved what we were looking to do. These are at the daily level, and here are all of our different statistics. All right, so that wraps up the data preparation. The main points here is that I have extracted all of the data that I'm going to use into DuckDB and prepared it somewhat. So I've taken that granularity problem we had, and now we no longer have to care about it. It's all stored, or the results are stored in our database, and we can simply pull that data out and use it as we see fit throughout our analysis and our kind of machine learning modeling. All right, so since we're done, I am going to close up the connection. All right, and the lock file has disappeared. We can now connect to this database with a writer at another point, like where we want to actually write data. All right, with the data prepared, and before I move on to my feature engineering notebook, I actually want to take you through one of my initial attempts. Now, the reason I'm doing this first is because during the competition, I actually jumped into this initial attempt, and I feel like I did it too soon. Like I didn't go through kind of proper steps of analysis. And I just wanted to show you what I tried out first. I think it is good to go over these kinds of attempts because it shows you my shortcomings, or at least shows you some of the mistakes that I made. So being a bit vulnerable here, the code is not great for it. And I think it's valuable to take a look at it, and you can learn a lot from kind of these, I want to say, attempts that didn't work out so well. So I think it is still valuable to go through this. But I wanted to show you this attempt first because it aligns better with what I was thinking at the time. I didn't do a lot of good analysis prior, and so I kind of jumped into things really quickly, which, as I say, was probably a mistake, or I think is a mistake, and I just wanted to kind of show that in context, basically. So opening up this initial attempts folder over here, there is this isolated series.py script, and I'll explain why it's a script and not a notebook in a bit. That's a funny story in and of itself. So for this initial attempt, my intention was to treat all 194 of the series as isolated series, basically treating them as independent series that I could forecast for. So they have no influence on each other. I didn't include any other features like the climate data or anything like that. I'm treating these as univariate time series. And for this, I used the auto-ARIMA model over here, and I'll touch on that in a bit. But the idea was to take each of the 194 different series that I need a forecast for, treat them as univariate series, get a forecast for them, see which series gave like the worst errors or had the worst performance, and use that as a kind of first attempt to my for the competition. Now, my initial code was a lot messier than this. I've tried to clean it up so that it's like a little easier to read, but I basically threw this together in like, a couple hours or something like that. I took it from my initial kind of messy work and made it as readable as I could. And yeah, let's just take a look through this guy. I think to make things easier, I am going to just wrap the code. So let's wrap it at like the first level over here and go through it like this, just so it's not super overwhelming. All right, for the script, I'm importing pandas, good old DuckDB, and then I'm using the package darts. Okay, so darts is a package which acts as an interface to all the different kinds of like time series type modeling packages out there. So to explain that a little better, it's kind of a one-stop shop for things like sklearn, for PyTorch, for different kind of libraries like stats forecast and that kind of thing. It kind of just brings all of those libraries together in a common interface, right? So instead of me having to worry about the way that stats forecast differs from, say, scikit-learn, I can just use darts as the common denominator between those two things and treat my data as the same between those two different packages. I don't have to care about the nuances of stats forecast. I don't have to care about the nuances of PyTorch. I treat everything as the same in darts. Now, this is specifically in the context of time series. So darts was put together as a time series forecasting type of engine almost for your scripts and for your analysis. So I think that darts needs its own video, but I will leave a link to the darts quick start. It's pretty easy to get started with. So if I open that up over here, yeah, time series made easy in Python. I actually used this competition kind of as an excuse to learn darts. I'd seen it around and I'd never tried it out. And I was like, hey, this is the perfect time to try this out. So I'd never used it before. I was pleasantly surprised by it. It was pretty easy to get started with. There are some weird complexities in it when you like get into the deeper stuff. But hey, if you want to see a video of me explaining darts in a bit more detail, let me know in the comments and I'll go ahead and make one. Yeah, but I'll leave a link to this quick start over here. And I want to mention the key difference or key, I want to say, object in darts, which is this time series type. So in darts, you basically can take a data frame from, say, pandas, and let me zoom in a little, make this easier to see. You can take a data frame from different libraries like pandas or polars or anything like that, and turn it into a time series type. Then once you've done that, operating on this time series type becomes easy in darts, but I'll illustrate that in a few. All right, with that said, I also import this concurrent .futures library over here, and specifically I'm using the process pool executor. We'll go through that in a bit. And then TQDM, I'm not using this to its full potential. I'm basically just using it so that I can get a cool status bar as I'm processing through all of the different time series. But there's more you can do with TQDM than just that. But that's how I'm using it at least. Okay, the first step over here is me creating this connection object. I'm connecting to the database. And you'll notice that this is kind of a global variable. I don't like this. I don't like this style of writing code. This was initially a notebook, but I turned this into a script. And again, I'll explain why that is in a few. But yeah, we connect to the database over here and jumping into, let's go to the main function over here. All right, the first steps I'm taking is grabbing our sample submission data frame from DuckDB. And this is as simple as doing a con.sql, select everything from our sample submission, and then DuckDB's API makes things, again, super easy. And you could just call this .2df over here, and it will take the result of your query and convert it automatically into a pandas data frame for you, which I find so cool. So with that being said, the other nice part is when you use 2df over here, it maintains the data type information. So when we use this to actually go and select the hydropower production data, I don't need to cast the date time as a date time explicitly like I would with the CSV. Instead, I've got that metadata in DuckDB already, and the data frame will automatically have a date time type or a date type in my data frame, which is pretty cool as well. It's also just another justification as to why I was using DuckDB as opposed to storing everything in CSV files. It just makes this kind of like import or input-output type of behavior a lot easier, in my opinion, at least. Anyway, the sample submission data frame is read, or we create the sample submission data frame. I then go ahead and grab the date and source. This is another part of the code that I should probably clean up, because I use this function so often. I should just store the result in DuckDB. I don't know why I didn't, but oh well. I'm just extracting the date and source information from the ID over here. And then when I go and grab our daily hydropower production data, I use this where clause over here to say where the source is in the sample submission source. So where source in select source from the sample submission data frame. Now, this is another cool part of DuckDB. I can just refer to my variable SSDF over here in my SQL query. So I don't need to go and convert it into a table or anything like that. In this context, DuckDB understands that I'm treating SSDF as if it is a table, which I think is cool. I just give it the name and it knows automatically what to do, which is pretty awesome. So I'm grabbing this and filtering it in the select to just grab the series that I need a forecast for, right? Only those that appear in my sample submission are the sources that I'm going to actually store in my data frame over here. All right, and because I'm pretty much done with DuckDB, for a safety mechanism, I close the connection and yeah, no longer going to use it. You know what? Actually, I was saying that I really don't like the connection up here. You know what? Here we go. Live editing happening right before your eyes. I'm putting this in the main function. I do not like global variables like that. So cool. Live edits happening. Awesome. The next step I take is to just select the columns of interest from our hydropower production data, which is date, source, and kilowatt hours. I then specify the min and max date as fixed variables. I happen to know these from the starter notebook, so just creating these two variables over here and storing them as timestamp types. I then specify the forecast horizon, which is 31 days, not 30, but 31 days, and store this as a variable. I then specify a variable called sources over here. Sources is equal to the unique sources in our sample submission data frame. I then set up an empty data frame, which will represent our forecasts, and a dictionary of results over here. So this is intended to store the source name and the root mean square error score that I get for that specific source. So this is a set of results that could be used for analysis down the way. I don't end up using these, but if you wanted to see which source had the worst root mean square error score or the highest root mean square error score, this would be useful for exactly that type of analysis. All right, then I just print a message here saying we're running parallel forecasts for this many sources. Now, this is where things get a little interesting. I basically take this process pool executor and use it to execute a function called forecast for source. We will go through that in a bit. Execute this guy with these arguments. So these arguments are passed to this function in parallel over here. And I'm storing all of this in a dictionary called futures. Now, the process pool executor is interesting because it lets you do parallel processes on your CPU. So it's one of these packages that lets you do kind of a parallel execution. Now, there is another type of executor called, I think it's called the concurrent or thread pool executor. Now, that lets you handle multiple threads, whereas this lets you run parallel processes. The difference is quite subtle. So the way that I think about concurrency versus parallel processing is via an analogy that I find useful. So I think about those kind of chess demonstrations. If you've ever seen a chess demonstration where you have like 10 players who play against one grandmaster, concurrency or multi-threading is kind of like that single chess player, that single grandmaster, playing against each of the 10 players by making a move and then moving on to the next board and making their next move while the first player is thinking about their move, right? So they kind of go around by giving their input, and while the other person is thinking, they move on to the next board, etc. So that's what multi-threading is. Now, parallel execution, on the other hand, is as if you had, let's say, 3 grandmasters playing against 10 other players. You would have a parallel process of 3, and then they could each multi-thread. So that's the way I keep it straight in my head. I always think about that analogy, and it helps me keep things straight. Now, the parallel processing is what you want to do when you have CPU heavy tasks, and multi-threading is what you want to do when you have I/O or input-output heavy tasks. In this case, this is a CPU heavy task because I'm not actually doing any input or output. I'm creating forecasts on my machine. That's CPU heavy. So I use a parallel executor. Now, here's why I made this a script rather than a Jupyter notebook. It turns out that on Windows specifically, and yes, I use Windows because I guess I'm an old man, but I found out that Windows does not cope with the the concurrent processing in a Jupyter notebook well, because when you try and spawn up multiple processes on a Windows machine, it will actually create multiple different Python interpreters. Now, this doesn't play nice with Jupyter because it wants to have a single interpreter. So running this in a notebook, this just kind of sat around like hanging and gave me no feedback whatsoever. So I was sitting there staring at it like, wow, this is taking really long. And it turns out this is a problem specifically on Windows. Now, on a Unix machine, or like a Unix-like machine, should I say, on like a Mac or on Linux, that's not a problem. It's only on Windows machines using Jupyter notebooks. So doing this in a script, no problem. Doing this in a Jupyter notebook on Windows, massive problem. So this is why it is a script. Anyway, that was quite a diversion. As I was saying, I am using this to run these forecasts in parallel just to make things a bit faster. Now, initially when I did this, it was just a straight up for loop doing each one in series. That took super long. And so I introduced this kind of parallel execution to save a bit of time. So with that in mind, I'll jump into the actual forecast in a sec, but just to show you, I then use this feature over here and then use TQDM over here to create a status bar to show you how far along the process it is. And if the forecast is not none, so per result that I get from this parallel execution, if it is not none, I actually get a result back. I then append it to my forecast data frame. So each one is now executed, and as I get a result, I kind of just concatenate it or union it into my forecast data frame. I then also store the source name in the results dictionary over here, as well as its root mean error score, and keep that for further processing. I actually, again, don't end up using results, so this is a bit, let's say, superfluous or redundant. But nonetheless, if you wanted to use the results and analyze which source has the best or worst root mean square error score, you could. I then take the forecast data frame. Once this is all complete, I've gotten returns for all of my different forecasts. I then go ahead and format the ID column. I do this by taking the index, which turns out to be the date. I actually set the index as a date, and convert this to a string, and then concatenate it with the source name over here with an underscore divider. So this is exactly what the sample submission CSV file or our sample submission table dictates we should have. I then do a set difference on the IDs between my forecasts and the sample submission over here to check that I've got all of the IDs that I need for a submission. And if that's incorrect, I print a message that say, hey, your submission is incomplete. Then I sort the values by source and date. You technically don't need to do this. I just thought it looked nicer, so I go ahead and do that. I also specify that I do this in place. So I'm operating on this data frame and I want it to take effect on this data frame as well. Then I save the forecasts to a CSV file. And if I wanted the results as well, I could simply convert this to a data frame and write it as a CSV file as well. All right, so that's the high level process. Now let's get into the actual functions themselves. Let's go ahead and look at forecast for source. What this does is it will take each of the different time series. So this expects one time series at a time. It will take it and it will actually it will actually filter the full data frame that you give it and filter it by the source that you specify. So now we end up with one time series. It then sets the data frame's index to be the date, and I then execute the forecast routine over here, passing it the single series, the single time series, the min and max date, as well as the forecast horizon over here. It then returns a data frame with a source column over here attached to it, so specifying which source it is, and gives me back the forecast itself, the source name, and the root mean square error score that we use downstream. All right, the real action is happening here in forecast routine. So in forecast routine over here, the first thing that's done is the single series is extended in terms of dates such that it has the full date range. Much like what was being done in the starter notebook, this ensures that the full date range from the min and max date is included in every series. So this takes the data frame and the min and max date, and then does this. So if we jump to this function up here, it will create a date range using pandas, so a daily date range, and then re-index the data frame itself over here with that date range. So basically like stretching it out if it does not have the full date range. If it already has the full date range, this will do nothing to it. So this just makes or elongates our different time series to the quote-unquote right length. All right, and then I thought I was being smart over here by taking the extended data frame and doing an interpolation. Instead of just filling it with zeros, I interpolate using a linear interpolator in both directions, so forward and backward. If there's any missing data, this interpolator will then go and do a linear interpolation on it. Now, this turns out to be a bad idea. And why this is a bad idea is because the lengths of missing data are so long that you get these kind of straight lines representing your data for these like periods that you've now extended the data frame to. And this biases your models like really badly, right? Because interpolators work well when you've got like one or two missing data points, but not so well when you're doing this for an extended period of time. So this was actually a really bad move on my part, but nonetheless, this is what I did, this is what I tried, and found out that later on, a hard lesson learned that this was a bad idea, and actually filling the values with zeros was probably the quote-unquote better move. But we'll get to that, and better moves than that in the later stages of this video. Anyway. From there, I then create a time series object over here using dots and simply use time series.from data frame and give it my cleaned data frame over here. And this works because I've set my index of my data frame to a date. So when you call this method over here and your index is a date, it will assume that that is the time component of your data frame and turn it into a time series that way. Then dots makes things easy because you can now do a train test split, much like you would do with like sklearn or something like that. And you can simply take or get the resulting training set and testing set using this time series dot split after the value over here. Now, this value is the length of the time series, so how many different data points I have, minus the forecast horizon. So I did this such that my testing set is 31 days in size because that's how long I want to forecast for. So I thought it appropriate to use 31 days per time series as an appropriate testing set. So the unique thing about time series, especially when doing this type of train test splitting, is that because time is a factor, you can't simply just split up your data by using like a shuffled set of your data. Time matters. So you have to use for your testing set data that is later than your training set. And dots makes this easy to do. And this is actually not so easy to do in sklearn because you first have to sort your data and really think about this kind of time dimension that's affecting you. This does it by default. So that is what this line is doing over here. I then set up my model, and this is AutoArima, and this is directly from Darts. So up here in the import side, this is from Darts models over here. It is just a wrapper around, I think it's PMD Arima, if I remember correctly. So you're actually using another library called PMD Arima under the hood. But what AutoArima does is creates an Arima model for you, but those parameters that I mentioned before when we briefly went through Arima, the P, Q, and D, or PDQ parameters, this auto selects them for you. So what this does is actually takes a look at your time series and then selects the most appropriate values that it thinks are appropriate for your time series. So this is really powerful, and like the de facto standard for when you're doing forecasting, this works as a great baseline model. So really powerful package here. I give it like no parameters. There are parameter options for it, like you can go ahead and look at the PMD Arima documentation for those parameters that you can set, but I just used the default over here. And Darts follows that kind of sklearn pattern of having a kind of train and predict, or sorry, fit and predict type of methods to basically train your model and then use it for prediction. So over here, I'm doing a model.fit on the train time series that we set up over here. So this is our data all the way up to, but not including the last 31 days of data. I create a prediction after doing that fitting over here and call this test forecast over here. And this is just by calling the model.predict, and you give it a forecast horizon. In this case, it's 31 units or 31 days into the future. And then I record a root mean square error score by using the metric root mean square error as provided by the Darts package. So they actually give you all of these metrics. So I import this guy from darts.metrics over here, and it knows how to calculate the root mean square error for a time series. So this just calculates that for the comparison between the test, the actual data, and our forecasted data as well. All right, when that's done, the objective of this was actually just to get a root mean square error score in the first place. I then create or repeat these steps for a full model, where instead of using the train test split data, I use the full time series, because now we're going to use it to create an actual forecast, not just calculate our error, but rather create an actual forecast that we want to use. So in this case, I give it the full data set, call predict on it, and then convert this back to a data frame by using this to data frame over here. So Darts lets you convert back to a pandas data frame or polars data frame, whatever you want. And in this case, I am converting back to a pandas data frame, and then I hand this back to our process. So effectively, this is a script which executes this kind of forecasting using Darts in parallel. And as you can see, pretty simple setup when it comes to the ML component. I'm just doing a fit and predict and using the time series as if they are univariate time series. No additional features, like no influence on each other, nothing like that. Just treat them as 194 isolated time series. Okay, with that said, let's go ahead and execute this guy to actually get a result. So let me go ahead and change directory into initial attempts over here. I am using my virtual environment, so this should work fine. Just take a look, isolated series.py. Okay, cool. Let's execute this and see if this works. All right, it prints out this warning message over here about Darts. Basically, there's different flavors of Darts that you can install. Oh man, and it's also like printing it out for every parallel process that I run. Oh geez. I try to get rid of that by using this filter warnings over here all the way at the top, but that doesn't seem to be working. All right, after about 5 minutes or so, I actually had to run this twice because there was a small bug in the code. I'll go through that. But after 5 minutes, this produces an output. The bug that I had to deal with was at the sort value step over here. The date column that I had prior, so what this looked like right before, If I just open that up. So the source and date columns were incorrect over there. The thing is that the date column specifically is actually an index, so I should have had this as the ID to sort the values. Not a biggie, but the other error that I picked up was just the pathing over here. My submissions folder is actually one directory up as opposed to being at the same level as the script itself. But we have gotten our output, so this should be in our ARIMA forecast.csv. So if I go ahead and look in submissions, I now have the ARIMA forecast file over here, and it contains our IDs and the kilowatt hour forecasts as well. All right, so let's actually go ahead and submit this guy. So I'm just going to go back to the competition site, Zindi, and get a score for our forecast. Alrighty, let's just click get a score for the ARIMA forecast. And we can see that, funnily enough, this does worse on both the public score and the private score. So this is not a good result, and you can imagine that when I started getting these results after doing like a bit of work with it, I couldn't beat the starter notebook, that this was disappointing to me. But we need to ask the question, well, why did it do worse? And when I go through the feature engineering notebook, which is next up, I think I have a good answer for that. So let's actually jump into the feature engineering, and I will return to why the starter notebook did a bit better than the ARIMA forecaster, given that the starter notebook had a fixed ARIMA model that it used on all the series versus the ARIMA forecast we just did used auto ARIMA and suited itself or best chose the parameters per series. So you'd expect it to do better, but we'll go through those reasons in a sec. So let's jump to the kind of next chapter of what we're doing. All right, with that in mind, I have opened up the feature engineering notebook over here in the repository. Let me actually close this up so it's a bit neater. There we go. Yeah, the feature engineering IPYNB over here. And this will take us through kind of more in-depth analysis of the data itself, as well as the climate data, which I didn't use initially. I just focused on the hydropower production data, which in and of itself was a bad move, of course, but this is just stepping through the data at a deeper level rather than kind of jumping straight into modeling, which I did during the competition. And as I said, I think that was a mistake. I should have gone through this step first of actually looking at the data, doing some analysis on it. This gives you better insight into what to do next with your data and what could cause problems for you down the line. With that in mind, let us run our imports. So over here, using the usual imports with the addition of sklearn, specifically the standard scaler, we'll be using that, and then some plotting libraries over here, matplotlib, as well as seaborn. Let's go ahead and import this. With that import done, we now go ahead and connect to our database again. This time I am not doing a read only like we were doing in the other script. This time I actually want to write the features that we create back to the database so we can use those. So this needs to be a reader and a writer connection. So I'm going to go ahead and run this guy. Right, with that in mind, the purpose of this notebook is to do some analysis on the data, as I mentioned, but more specifically to produce features as well. So producing features that are intuitive, basically thinking about like, well, what would affect power production, and trying to create those features and then look at them in terms of correlation. Also to visualize the data. I mean, up until this point, we've seen like one plot of what the data looks like, and this was a critical mistake by me as well. I didn't visualize the data soon enough to actually see the overall trends. So this will be useful for us to actually see what's going on in the data itself. And then also checking covariates or covariation in the data. So we'll be using the Pearson correlation. But this is an important step to see which data influences which, or which features influence each other, and more importantly, which features influence the target of kilowatt hours. All right, but to start things off, I am going to go ahead and grab our data. This time I'm grabbing everything. I'm putting it in a data frame called DHP, or daily hydropower data underscore DF, or data frame. So I'm selecting everything from daily hydropower production. Right, and we can take a look at the head of this guy to just see the data itself. This is exactly the data that we are looking for. Then to do a .info, we can also see that this data has 136,000 records as opposed to the initial 39 million. It takes up way less space in memory, so a lot more palatable, I suppose you could say, by your RAM. And our data types look correct. The date is a datetime type. The source is an object. The consumer device and data user, these are stored as objects. You could store these as integers as well, because these are integer numbers, and those would probably be a little more memory efficient. But since the data is reasonably small, this isn't too important. However, the kilowatt hours target variable, it's important that this is a floating point number, or considered a number, because we are going to do operations or numeric operations on top of it. So it's important that that is a number. These two could be either an object or an integer, depending on your preference. All right, let's take our data and actually aggregate it at a high level. Since we're dealing with so many different time series, it's really intimidating to try and visualize each one individually. So instead, what I'm going to do is aggregate the data across the different time series or over the different time series so that I just get an overall trend. So a single time series that represents the overall trend of hydropower production. To do this, I'm going to take the date and kilowatt hour columns and group these by the date. I'm not going to set the date as the index in this case, and I'm going to take a sum across the kilowatt hours. And I'm just storing this in a variable called aggregated daily hydropower data frame over here. Let's go ahead and run that. And then I'm going to use the .plot method from pandas directly just to plot this at a high level. So the idea here is just to plot the date on the x-axis and the sum of kilowatt hours across our different time series on the y-axis. I'm making this plot reasonably big and just giving it a title so that it looks a little nicer, I guess. Let's go ahead and run this guy. And this gives us the overall trend of our data. So a few observations here. Looking at this, it seems like the data goes from 2023 as expected. However, there's a significant period of zeros over here, or very small signals potentially over here, and then a few bumps that happen. Then all of a sudden in October 2023, things start picking up and power is being produced by the micro hydropower plants. And all of a sudden in January 2024, there is this significant period of no power being produced, right? So this means it's not just one or two series that suffer from this. Almost all of the series have this kind of behavior of having no power produced between January of 2024 and July of 2024. So there's this period of just no power. And then all of a sudden things pick up again. Now, looking at this, we can hypothesize as to the reason for it. What could have happened is that this project could have started out with just a few micro hydropower plants. So these could have just been installed, like a few of them producing a small amount of power, and then suddenly a bunch more getting added to the network of the hydropower plants and them producing power. Then this period of downtime, interestingly, when we look at the weather data, this is kind of a time, or kind of the winter period in Kalam. So you could hypothesize that maybe all the water is frozen over here in the different rivers and such where the micro hydropower plants are, and so no power is produced. So looking at this data, this period over here affects us because if we think about what we were doing in the isolated series script, when we extend our time series or even just look at our time series at a high level, we have all these zeros over here. So there's like very weak or zero signal over here. And when we extend that, or extend every time series to be across this full period of time, some of them don't extend to this full time period. And when we do an interpolation, we are interpolating a large amount of data. And this is problematic because that interpolation becomes data, right? When you do an interpolation, you are basically filling in the blanks with synthetic data. And this becomes problematic when you hand it over to a model, because your model actually learns that synthetic data, right? So this is part of the reason why my initial approach in the isolated series script was bad, right? I didn't look at the data and didn't see how much data was missing and how much data I was actually interpolating. I was just kind of following this path bluntly. Whereas now this tells us a completely different story, where we have a significant downtime in power production and need to deal with that. So important for us to actually just observe trends in the beginning or as soon as we can. So yeah, mistake on my part, and hopefully a lesson learned for yourselves. I'll definitely take that lesson forward, that visualizing your data first is really important so that you have a good idea of what's going on. All right, with that in mind, let's go ahead and grab our sample submission data here. Just grabbing that from the database and then extracting the data in source again. Again, I should have just stored this information, but Oh well. Cool. With that, I also am just doing the high-level observation again that the amount of series we're dealing with is actually 585, but we only need a forecast for 194 of those, so just pointing that out. And then taking into consideration the devices to drop from the starter notebook. So I'm going to include these. So I've just stolen these from the sample submission notebook, and I'm going to remove them. Just so, once again, so I reduce the problem space or reduce the number of series we're dealing with. So I'm going to go ahead and drop these guys out. And to drop them, I store their different numbers, the device numbers. I store them as strings, right? Because in my case, I've stored these as an object type or string type. And to actually filter them out, I'm going to use them on the consumer device column over here. So I'm going to create a new data frame called toForecast data frame and take the hydropower data frame over here and then make a filter where I say if consumer device is in the set of devices to drop, and then use the not operator. So I'm saying all those series that are not, or all those records that are not having consumer device in this list over here, create a copy of those into forecast data frame over here. All right, so let's just execute that. Then I still want to make my data the same lengths, or my time series the same lengths, but I found an easier way to do this than the kind of way that I was doing prior, which was like in a loop, extend each and every data frame and then concatenate it. Instead, to make this cleaner, I use a pivot function. So how that works is that I'm going to pivot, and actually let's take a look at the data. This will make it a bit more clear. Let's actually add a step over here. So toForecastDF.head over here. We know that all the different series are kind of stacked on top of one another. If I pivot these and pivot them by the source column, I'm going to get a data frame or a resulting data frame that has the same number of columns as there are unique sources. So this is going to pivot this column into, this source column, its values into columns themselves. So I'm basically going to swing these out as columns. So I should end up with a data frame with as many columns as there are unique sources, and instead deal with each of the series that way. If I run this, it'll become more apparent what the pivot operation is doing. So over here, I now have a data frame with 421 columns, which is how many different sources we have left after doing that devices to drop type filter. And you can see we have the date over here, and then each source now has the kilowatt hours in them. So the pivot operator is quite useful in this way, and this guarantees that all of my different series have the same length. So now I want to get back to the kind of stacked version of this, so stacking the series on top of one another. And to do that, I do the reverse of a pivot, which turns out to be a melt. In other programming languages or other tools and stuff, this might be called an unpivot, but in this case, in pandas, it's called a melt. And so I'm going to melt these back into row values again. So this pivot and melt type operation is just a faster way, or in my opinion, cleaner way to make sure that the series of different lengths are now all the same length. So let's go ahead and run that. And this brings us back to a data frame where we have our different series all stacked on top of one another, but they all have the same length now. All right, and now I'm doing a bit of a kind of rework over here where I'm just taking an aggregate by date again. I could technically have used our aggregate from earlier, but anyway, I'm just creating a new data frame over here called the power DF, which is the toForecast extended data frame, which I called this guy over here because we extended all the different series. And I am taking this and grouping it by date again and taking the sum. So exactly what we were doing with the aggregate earlier. I could have just used that data frame, but oh well. Redoing it. And now I end up with a data frame that's just a single time series rather than multiple time series. I then go ahead and grab our climate data. So over here, I'm doing a .SQL, selecting everything from the daily climate data that we have and converting that to a data frame using toDF. Let's just grab that and look at the first few rows. And this grabs our data as expected, our climate data. Now, given the climate data, I went ahead and created different climate features associated with the climate data itself. I also do temporal or time-related features, but we'll get to those in a second. So over here, I'm creating new columns in our climate data frame Those being the temperature due difference. So I was basically just applying like some intuition. I also kind of took these from example notebooks that other users had presented. So some other users shared their notebooks, and I took the features that they were using that I thought were cool and stole them for myself, basically, in this. So one of them was the temperature due difference. So this is the difference between the average temperature and the dew point temperature. The wind speed, you can calculate this from the u and v components using like the squared u component plus the squared v component, all square rooted over here. The precipitation to snow ratio is an interesting one because you take the total precipitation, because this turns out to be not just rain, but also snow as well. So if you take the precipitation to snow ratio, you are effectively getting a ratio of kind of like rain, or the total of it that is not snow, right? So if you take a ratio of the total precipitation divided by how much snowfall contributes to that precipitation, you are getting a ratio which represents kind of rainfall, which turns out to be very useful. Now in this division, I am also adding a small number to the denominator in case there is a zero. I don't want to get a divide by zero error, so I just make this a small number instead of it being zero. Then precipitation minus snow is very similar in idea. All it is instead of a division, it's a difference between the total precipitation and total snowfall. Then there were some more kind of like, I want to say out there features that I was trying that I just thought would be cool to test out. There was the rolling sum of precipitation over 7 days. I do this by taking the total precipitation using this dot rolling method over here and do a dot sum across that. So if you give dot rolling an integer value, it will take a sliding window of that period of time, in this case 7 days, and do a sum across those. I do something similar with the snow over 30 days over here. And then there was another feature over here called melt potential that I tried out. My logic there was something like, well, if there was a lot of snow, but the temperature is increasing, the snow will melt, there will be a lot of water, and so a lot of power will be produced. So I wanted to try this out, basically taking the multiplication of the average temperature times the average snow cover percentage. So the higher the temperature and higher the snow cover percentage at that time, the higher the melt potential was the logic. And then finally, the wind variability. This is also a rolling metric over here. I roll over 3 days, but instead of taking the sum, I take the standard deviation over here. So it's how much the wind varies over 3 days that I'm looking at. So just thought those were kind of cool. Just applying kind of intuition and brainstorming these kinds of things. I just basically produced these features and was going to see which stuck basically, or which were actually useful. So produce a bunch of features and then try them out and see which are actually valuable was the strategy. So let's run this and get our features all on the climate data frame. Then I also had some more time-based features. So these are temporal or time-related features, and these included things like the day of year over here, so the actual day number of the year, the month of the year, so a number associated with the month, and then interestingly, the sign of the day of year. So this is a sine function applied to the day of the year itself. So you basically get a sine wave across the year and a cosine underneath this over here. So you get a cosine wave of the day of the year. Now, this is interesting to explore seasonality and is typically used to look at seasonality. If something has got a seasonal pattern that looks something like a sine wave, this can be quite powerful, basically like something that flows like a sinusoid across the full total year. Then after all this feature engineering, actually, let's run this first. And after all this feature engineering, I merge the features back onto our power data frame. So I merge these two together, the climate data frame and the power data frame. I join them on date, and I do a left join or a left merge because the climate data frame turns out to have more dates in it, or a more kind of complete set of dates than the power data frame. So the left join is such that I capture all the date information. Even if I don't have power for or power data for specific dates, I still want to see the climate information as well, just to look at the overarching trend. And that's why I used a left merge over here, or left join over here. So over here, we get all of our features basically. And right at the end, we have our kilowatt hours. And yeah, like I was saying, the climate data frame has more dates in it than the power data frame does, and that's why we have a bunch of missing values here now, but that's okay. All right, now for plotting, I wanted to see the overall shape of these features against the power production information. So to observe the shape, one of the challenges is that the scales of all these different features are, well, different, right? Temperature can range from like 1 degree Celsius or like negative degrees Celsius all the way up to maybe 40 on like the hottest day, like 40 degrees Celsius. Whereas something like the kilowatt hours can range from like 0 to 2000. So the scales are completely different. So to visually inspect this, they all need to be put on a consistent scale so that there isn't this huge difference between the scales of the features and the target variable. To do this, I use a scalar, and this is where we are using the scikit-learn standard scalar over here. You could also use a min-max scalar over here. I just kind of arbitrarily chose the standard scalar for this reason. So I first instantiate a scalar by calling the standard scalar. I then grab all the numeric columns, so I only want to apply this to columns that are of type number over here. So this is selecting all of the columns that are of type number. So I'm taking the all data frame and selecting the data type number or number type columns, and then getting their column names by using dot columns over here. I then create a copy of the all data frame over here because the schema is going to be the same. So I create a copy of this and store it in a data frame called scaled data df. Then I take the numeric columns from scaled data df and apply the scalar to it. So scalar.fit transform on this actual data over here. And so I'm storing a scaled version of all the numeric data in these columns over here in scaled data df. So run that. This will rescale our data so that it's easier to observe kind of shape-like patterns in the data or see the data on similar scales rather than on these really widely varying scales. Then over here, I'm just defining a variable called feature columns to store the features that I'm interested in. So this would be all the columns except for date and kilowatt hours. Those are not features that I want to observe. This is the target, and date is rather just like, the date itself. And I don't want to look at that as a feature right now. I've created time-based features already. I don't want date to be included in my feature list. So this is just creating a list of columns that are the features that I'm interested in. Now with that, I go ahead and plot all of the features against the kilowatt hours over here. So I'll go through this code in a little more detail, but the idea is to create a series of plots that represent all the different features against the kilowatt hours over here. So I am going to jump to this section over here. And what I'm doing is using matplotlib subplots to set up a frame or a figure with a number of plots or a number of figures in it. So in here, I say len of features because this will give me the same number of, I want to say, rows in my subplot as there are features, and the same number of columns as there are target variables. In this case, there is only one, so it's going to be a subplot of just like one long list of different different plots, should I say, over here. And I make this quite big to fit everything. And I'm specifying share X as true because I want them all to share the same X axis at the bottom, just to save space, right? And they all share the same X axis. This is going to be time, right? I'm going to plot these against time. They are all going to be plotted against time, and so they share a common X value, hence why share X is true over here. I then create a super title, so an overarching title that just makes things nicer to read, give it a nice big font size so that it stands out. And then I loop through every feature over here. Now, I'm using enumerate here because I want the index and the feature itself. So that's what enumerate will do. It unpacks an index, so going from 0 to the length of the features, and then also gets the features themselves. That's why I'm looping with an enumerate over here and not just looping through features. I then select the plot, so that's what the index is used for. So for the first plot, it'll be index 0, so it's like the first subplot that I want to plot on, I'm selecting over here. I then go and plot the date as the x-axis and the feature that I'm talking about and label it with the feature name. I then also plot the date and the kilowatt hours and label it as kilowatt hours. And to differentiate the two, I change the line style of kilowatt hours to a dotted line rather than a solid line, just to make it more apparent as to which kind of series I'm looking at. I then make the y label the feature name, And if the index is the last index, so the len of features minus 1 over here, I then add an X label. So I don't want every plot to have the label date on it. That just would take up unnecessary space. I just put the label date on the last plot. And then if it's the first plot over here, I wanted to have the title total kilowatt hours over here. Then on every plot, add a legend in the upper right corner, and then swivel the x-axis markers by 45 degrees. So it's like when we have dates, it's a little hard to read if they're all like overlapping on each other. The 45-degree rotation just makes it more readable. And then this tight layout over here just saves a bit of space. It's not too important to include, but yeah, that's why I included it. And this is just a plt.show to actually do the plot. So let's run this, and it'll probably make more sense when you can actually see what the result is. And over here, this is our plots of each of the different features against the kilowatt hours over here, or the overall kind of sum of kilowatt hours. And these are all scaled, right? So these have all had the standard scalar applied to them. And so I'm less interested in these numbers on the y-axis. Instead, I'm more interested in the shape matching over here. And this repeats for each and every feature over here, just to look at the overall, once again, the overall trend compared to how much power is produced. So the ones that are interesting are, for example, like temperature. If I observe this, I can see that a increase in temperature in 2024 at least, which is the right-hand side over here, an increase in temperature corresponds or correlates with a increase in power production. This is not true in 2023, funnily enough. Like the temperature decreases and we're still getting power produced. So a bit of a weird one there. Then if I scroll through, the precipitation is an interesting one as well, because in the time period where there's not a lot of power being produced, we can see sudden spikes in total precipitation. But there is a bit of correlation over here where we're getting precipitation and power is being produced. This becomes more apparent as well if we look at average snow cover, because during this time period, the snow cover is high, right? And that implies that it's winter time over here, or at least you could infer that it's kind of winter time at this point, and we're not getting a lot of power produced. Funnily enough, again, in 2023, this is kind of like a weird contra case where we have a lot of snow, but power is still being produced over here. But the feature that I do want to point out is the precip to snow ratio and precip minus snow. So if we look at 2024 specifically, there is high correlation between the power being produced and the precip to snow ratio, or precip minus snow. So this makes intuitive sense in some ways, because it's like if there's a lot of rainfall, that means a lot of power is going to be produced by your micro hydropower plants. Of course, this doesn't explain 2023, which is a bit more challenging. It seems like over here the snow is okay, and you're still getting power even with the snowfall. But in 2024, this isn't the case, right? It's like the rainfall seems to be the main contributor. And you can go through and make similar observations about each and every one of these different features, going through the various plots over here. Of course, there is the kind of temporal features over here, like the day of year. As this increases, so does power production, which shows you some seasonality. Similarly with months. And then sine day of year is like somewhat interesting. It's kind of like inverted. So when you have a low sine day of year, you have high power production. And when you have a high sine day of year, you have almost no power production. So there's something going on there. But yeah, these just show you the overarching trends and comparisons between each of the features and your target variable. So I just noted down some observations over here from these plots, noting the downtime between January 2024 and July 2024, the precipitation minus snow being quite coincident or quite correlated with power production. And then in 2024, snowfall does not seem to have an impact, whereas in 2023 it kind of does, which is interesting. And the temperature rising in 2024 coincides with power production as well. So there's clear seasonality in this power production, and the temporal features like the sine day of year or day of year does reflect that as well. Like it's clear to see, at later time periods in the year, it seems like there is higher power production. So that indicates seasonality to you. Now, the next thing that I do is to actually look at lags or lagged features, right? So maybe maybe rainfall today or rainfall at the same time as power being produced is not significant as, or not as significant as the rainfall that happened last week. So if you think about that, it means that, like, if I were to consider something like the rainfall from last week, intuitively it makes sense that the rivers would be fuller, and then maybe I only see the effect of that later on. So when dealing with time series, you can observe lagged effects, right? So it's like, because rainfall was heavy last month or last week or something like that, then I get a lot of power because my rivers and water catchment areas are fuller. So this is an interesting part of time series, and I say interesting as a euphemism for challenging, that these kinds of lags and leads become significant. Like, the effects of what you're observing may only come to fruition at a later stage, not at the same time as what you're observing. Now, with that in mind, I wanted to actually see if there was any of these kind of like lagged indicators in the data. So like, if I lag rainfall or if I lag temperature or anything like that, does that effect only show up later in my kilowatt hours produced? So to do that, what I do is take all data df, I first sort it by the date values, and then just print that out to make sure that my data is sorted appropriately. And then this block of code, I'll explain this at a high level, but what this does is takes different lags. So I've labeled these as like 0 lag, 1 day, 1 week, and then given a number that represents that lag. So for example, 2 months is about 60 days, a month is about 30 days, and a quarter is about 90 days. I then go through all of the different features and shift the values by the lag over here. Now, significantly, what I'm doing as well is I'm filtering the data for 2024 only. The reason I decided to do this is because this is where we're going to do forecasting. So I'm placing emphasis on the 2024 data and only observing these effects for 2024 onward. I'm kind of ignoring 2023 because of like the weird complexities with it. So I decided to try and make my life a bit simpler by basically chopping it out and ignoring it, which could have been a mistake. That could be a bit of a cheat or a bit of a, bit of laziness on my part, but hey, that's what I did. Anyway, so I shift the features by the amount of lag that I'm interested in. I then take a correlation of those shifted features with kilowatt hours and store this in a data frame, basically. So I just went through that at a high level because it's a bit confusing to explain all of this. When I show you the plots, it'll become more apparent what this code actually does. So plotting this out, I plot out the different kind of correlations as a heat map in Seaborn, and this shows the Pearson correlation. So this .core function over here, or this .core method in pandas, uses the Pearson correlation, which is a straight line correlation by default. So let me print out the heat map and use that as kind of a visual guide as to what I mean. So this plot over here has all of our different features and then the various lags of those features. So if I look at, let's say, average temperature over here, let's look at this one, the third one over here, and draw a line down here. This is the average temperature lagged by a week, and what is the correlation between that that value and kilowatt hours? So the lagged feature correlating with kilowatt hours produced. And these values in the actual blocks represent the Pearson correlation. So the Pearson correlation is, as I say, a straight line correlation, which means if it's heavily positive, it means that there is a relationship such that if 1 increases, so if average temperature increases, the 0.5 over here being like reasonably strong or reasonably close to 1 means that as average temperature lagged by 7 days increases, so does the kilowatt hours produced. So that's what a higher number would mean. If they're negative, it means that they are negatively correlated, meaning that as one increases, the other decreases significantly. So this shows you these kind of straight line relationships between them. Now, the thing with correlations is that they should be treated as kind of like a compass rather than the map itself. Now, what I mean by that is correlations can tell you where there are relationships, but they don't tell you why those relationships exist or how they came about. I'm basically describing the correlation versus causation argument, live, but it's a cliche for a reason, because you can misinterpret this to say, well, because temperature rose, that is why kilowatt hours produced increased. But it might be that temperature rose, melted some snow, and then that's actually why the power was increased. Or it might be that because temperatures are higher, people are running air conditioners or something like that, and so needed more power in the first place. It tells you there's a relationship, but doesn't tell you what the relationship is. So this is more of like, as I say, a compass or a rough guide rather than the actual descriptor of the relationship itself. Anyway, getting ahead of myself, these features and this correlation plot kind of gives us an idea of where to look for relationships, basically. So I'm going to skip ahead just to the observations over here. And it was clear to me that at features at a lag of 30 days or about a month seem to be good candidates, or these features seem to be good candidates at about 1 month. The temperature / dew point temperature is a good candidate, the wind speed, the precip minus snow or rainfall over here, and the precip to snow ratio, precipitation to snow ratio. These showed significant correlation with our target variable. Now, some of them have strong correlations, like those involving snow, but looking at the signal plots, these could be spurious or like random relationships, and they don't really make intuitive sense. A good one is looking at melt potential. At a lag of a quarter, so 90 days, it has a very positive correlation with kilowatt hours produced. So it looks like a good candidate, but the thing is, if I look at the actual plot, let's find melt potential over here. Where is this guy? There it is. So looking at melt potential, if I lag this by like 90 days, that's basically shifting this forward. It's like, of course there's a relationship, because now you are like putting the spikes on top of the other spikes. But what is that really telling me? It's kind of like, well, maybe there was a lot of snow 3 months ago, which is rather telling me that the feature should be something like, well, 3 months ago was probably winter time. So instead, this should be a season indicator or something like that to say, is winter, is not winter, and that's what the relationship truly is. And saying this out loud, having a season feature like that would have actually been a really good idea. And I'm realizing in real time that I should have paid more attention to my feature engineering and tried something like that out. Well, hindsight is 2020, but you get the idea. Like, some of these relationships might be just random, right? Or indicating something else to you rather than a pure relationship between the two variables. All right. With that in mind, I'm pretty happy with the features that I've generated. We've looked at some of the relationships. We've looked at the data itself and actually done some analysis on it. We have a better idea of what's going on in the data. With that in mind, I'm going to now store all those features that I worked so hard to create. I'm going to store them as a new table in our database called daily features over here. And I'm selecting everything from the climate data frame. So this does contain some duplicate information, but that's okay. I just want to, more importantly, store the features that we generated. And so I'm doing the typical move of create table in the prepared schema. And this is just a select star from our data frame over here. Let's run that. And since we are basically done, or at least I'm done at this, I'm now going to close the connection to our database. Now, before I move on to my kind of final solution and how I actually used these features and kind of decided amongst these features which to use, I wanted to take you through one of my other initial attempts. Again, this is kind of messy and it didn't work out super well. I didn't actually end up using it, but I think there were some cool lessons in it and some cool ideas that if I'd used a little more or pursued a little more would have really helped me out or could have made something interesting. So I just thought it would be valuable to share. So I'm going to jump back to this initial attempts folder over here and go ahead and open up the notebook clustering series over here. All right, and the main idea of this notebook over here is that I was thinking about how do I kind of get around this problem of having so many series to deal with, these kind of issues of bias and that kind of thing in the series. They all have different lengths, as we observed from the analysis we just went through. How do I deal with all of this? Because it was really overwhelming to have all of these different series, they all behave in different ways. I've kind of observed features at a high level and the kind of kilowatt hours produced at a high level, but I wanted to understand, like, is there similarities between certain sets of these time series? Like, are there time series that are similar to one another, and could I use that to my advantage? And my main idea here was I wanted to cluster them together, and I will take you through that. Basically, extract features that are relevant to the different time series. Like, are there time series that are the same lengths? Are there the time series that have similar mean values and that kind of thing? And put them together in similar clusters so that I could perform more specific analysis. Like I said, this didn't end up working for me, or I didn't pursue this fully, but I wanted to share it nonetheless. So with that in mind, I go ahead and do my imports, and I am adding an interesting addition over here, and that is this package called TSFresh over here. This is an interesting library, and I think is, yeah, really cool. I came across this for exactly what I'm describing, extracting features from multiple time series. And I'm importing a function called extract features, right, from there. So if I go ahead and run this just to get all of our imports done, I then go ahead and connect to the database. So pretty stock standard at this point. And over here, I explained the idea that I explained to you, basically that I wanted to reduce the number of problems that I was dealing with. But basically, the first steps I take over here is similar to what we've done before, getting the kilowatt hours data or the power production data, but only considering those that I actually forecast for. So doing this kind of sample submission, using sample submission as a filter. So a very similar idea to what we had in the isolated series script. And then over here, I'm using the extract features method or function over here to actually extract features from our multiple time series. So with TSFresh, you can specify a custom set of settings. And part of this is what statistics you actually want to extract from your set of features. In this case, I chose pretty simple ones: the mean, standard deviation, the kurtosis, as well as the skewness. The length is how many data points I have. I also thought about using the autocorrelation, but things get complicated with autocorrelation, especially when you're not sure whether or not your time series is actually stationary. So this is not like super valuable, but you know, could include this, uncomment this, and include it. And then the ADF, or augmented Dickey-Fuller test, is actually a statistical test to check whether or not your values, your series are actually stationary. But the TSFresh package will give you a ton of features. So if you don't specify these custom settings, it has like, I think like close to 700 different statistics that it can produce, and it will give you all of them. So I was getting overwhelmed by that, and so specified a custom subset of statistics that I wanted to look at. Then using this extract features function over here, I pass it my data frame of all my time series. I specify an identifier for the series. In this case, it is the source marker. The sort column is date, so kind of our time column itself. And the column value that I'm interested in doing these statistics on top of is the kilowatt hours column. Then the progress bar just shows me how long it takes for it to process all of the series. So I just thought that was kind of cool. And then I specify default FC parameters just as my custom settings to limit how many different statistics it actually looks at. Let's actually go ahead and run our feature extraction with TSFresh. So let's go ahead and run this guy. There we go. The progress bar showing me how long it takes to get a hold of all our different series. All right, so that completed reasonably quickly. So TSFresh's output basically will list your different series over here as your index. So this is specified as the output data frame. So the output data frame is this features df over here. The index is the various labels that you've specified, or IDs that you've specified. And then per each of those IDs or each of those series, we now get the statistics we look for. So it names it like this: kilowatt hours __ mean. And this is the mean value of the time series that we're looking at. And scrolling to the side, it has all the other statistics that we specified over here. So like the length, how many data points we have, the skewness or measure of skewness, and the ADF test results over here. Now this one's a little weird. The augmented Dickey-Fuller p-values, basically. Effectively, if this is like below about 0.05, it can be kind of the null hypothesis of it not being stationary can be rejected. That's a complicated way of saying like, well, it's basically stationary. But yeah, that's what this result is. The rest are pretty standard kind of statistics. This is just one of the weird ones. Anyway, we can now plot out our statistics, right? And it's a bit easier now that we've actually extracted them. I can go ahead and use the features data frame we just created and plot it. And in this case, I'm using a histogram to plot out the various means of the power production data. So printing that out, then get a frequency distribution or a distribution that looks like this. And it shows us clearly something that we kind of did already know, but the extent to which we knew it is questionable. However, what I'm pointing out is that some of the means, or majority of the means, should I say, or majority of the time series have very low means, and there are a few outliers out here. And really the range is that there are some time series that have means up to about 20 kilowatt hours, so an average production of 20 kilowatt hours, versus the majority that have means somewhere between like 0 and about, I'd say 2 kilowatt hours over here. The main point is that I can now plot out any feature that I want. You can substitute this Y value for any of the others and get a distribution plot, or make some other plots with these. It just makes things a bit easier. Now, the the kind of out there approach that I took, or kind of a strange approach that I took, was that I wanted to take these features and use a k-means cluster on them. So I will leave a link to one of my videos where I go through k-means clustering in a bit more detail, but I'll go through the basics over here. Effectively, I'm taking our features and scaling them. So features df, I'm also filling any NA values, which I don't think there are, if I'm not mistaken, but just in case, filling any null values with A0, and then applying a standard scalar to this. And the reason for that is when you're doing k-means clustering, you want your different dimensions to have a similar scale, such that the clusters are not biased towards values that have high ranges. So for example, if a particular value ranges from 0 to 1,000 versus another value that ranges from 0 to 1, there's going to be a bias towards the value that ranges from 0 to 1,000, right? The influence is much heavier, or movements are much more drastic on that scale. So we scale all of them and store this as its own data frame over here called scaled features df. Then I set up different objects to contain our scores. We have the inertia values for our clustering algorithm, our silhouette scores, and various values of k. So in the k-means clustering example, you have to specify k. It's a free parameter. You need to specify how many clusters you want, and you determine how many clusters you want by evaluating the inertia and silhouette scores. So I just go through a loop over here of setting up a k-means cluster from scikit-learn, the pretty typical k-means algorithm here. Specify the number of clusters as k. So I'm kind of looping through all of the various values of k. I'm ranging from 2 clusters to 10 over here. So remember, range is exclusive, so it'll go up to 10, but not include 11 over here. I specify a random state or fix it to 42, just so that we have reproducible results. I also initialize the centroids for the cluster as auto. I then store the labels that we get over here, because this will be the cluster numbers that we assign to all the values. That's the label result. That's what we're looking for with the k-means cluster. And then append our scores, the inertia and the silhouette scores over here, so that we can evaluate our values of k. I then plot out the inertia and the silhouette scores. The inertia is typically called an elbow curve, and you'll see why in a sec. And then I do something similar with the silhouette scores, just basic plots over here, so that we can evaluate how well our various values of k are doing. Okay, am I getting this error message? That's weird. Oh, okay. I think that was probably because I actually have no idea why I got that error message. Anyway, well, running it twice makes it disappear, apparently. All right, so looking at our elbow curve over here, it's clear why it's called an elbow curve. It looks like your elbow, I guess. And what you want to find is where you are getting the most drastic changes, or the drastic changes are stopping. So the gradient kind of slows down. So clearly from 2 to 3 is a big jump, from 3 to 4 is a big jump, from 4 to 5 we're kind of slowing down, and 5 to 6 not much change, right? So just looking at the pure elbow curve over here, 5 seems to be an appropriate number of clusters. And then evaluating the silhouette score, which tells us how much overlap we have in the clusters. We want to maximize this value, so 5 looks like a clear winner. So 5 clusters seems to be appropriate. Now, if this was confusing again, I'll leave a link to my k-means clustering video. I explain this in a lot more detail and go through another example where clustering is a little more clear to use. Like, this is a bit abstract. I'm clustering time series features together and trying to figure things out, so it's a little abstract. If you've never seen this before, I'd recommend checking that video out. All right, so we've determined 5 is our most appropriate number of clusters according to this data, at least according to the features that I selected. So what I'm going to do is create a new k-means cluster with setting k to 5, random state 42, init, auto, all of the same parameters that we had before, and just selecting or fixing k, getting our cluster labels and adding those cluster labels back to our data frame. Now, actually, I think I've made a mistake here and assigned the cluster value to the scaled features. You don't want to add this to your scaled features. You'd rather have it in features df. Let me actually fix that right now. So features df cluster, yeah, cool. Let's run that. Okay, that runs perfectly fine. Then I want to go and plot out my features per cluster. So I want to compare what my clusters look like across the dimensions that I have, and I'm going to use violin plots for this. This is pretty much what I did in my previous video, so same idea. And let me replace this with features df instead of the scaled features. Okay, I'll need to push these changes. That's okay. Let's go ahead and run these. Okay, yeah, and the reason I wanted to use features and not the scaled features is because it makes this more interpretable. Like, I can now read my mean values as the actual mean values, not scaled mean values. Like, if I had the scaled values, I'd have to like convert those in my head, which is not great. So I would prefer to have the actual values on my plots. And I'd go through the normal kind of analysis here, saying that clearly cluster 2 contains series that have high means, cluster 1, 3, and 4 have lower means with a bit of spread, and then 0 has those with moderate means in them. So that's the split in terms of mean. Then looking at standard deviation. So unfortunately, our high mean values also have a high standard deviation, right? And the others have moderate standard deviation. One clearly has high kurtosis. One also has high skew, etc. Like, I'd go through this full analysis, kind of comparing them piece by piece. And then the augmented Dickey-Fuller test, these are just p-values, like, which are stationary. Like, it looks like 1 and 3 probably are the most closest to being stationary. Yeah, this isn't great, I'll be honest, as a feature for clustering. I would remove this, you know, looking at this in hindsight. I would use this rather as like I want to say a binary split. So do the ADF test and split my series into stationary and non-stationary, and then do analysis on those separately rather than kind of using it as part of my clustering. This is a bit weird. Anyway, that expresses the clustering kind of idea. I'm going to close the connection here. And just to go through the lessons learned, yeah, I literally just said I should have either abandoned the ADF test or used it for a binary split. That's one of the lessons learned. I could have used these features like mean length and standard deviation to group the series into different training sets for different models. That was kind of what I was leaning towards, but as I said, I kind of gave up on this early. I wasn't getting anywhere with it. I was just getting frustrated, so I abandoned it. And yeah, but if I'd pursued this, I could have used it for an interesting kind of training data split. And maybe if you want to try it out, you could use something like this to split up the data. And yeah, given the groupings, I could have used different models to make a powerful ensemble model. Like, I could have used these different training sets, produced different models, and then ensembled the models together, basically combined individual models together to make one super powerful model. And we'll go through this in the winner's solution briefly, the kind of power of ensembling models together. So I think this method is powerful, but you really need to critically think about what your objective is. I was kind of just pursuing this somewhat blindly again, just trying something out like fast as possible, see if I could get anywhere. And I didn't end up using this, but I was just pursuing this on a whim. So before going into analyses like this or going into different kind of experiments like this where you're going to spend a lot of time, expend a lot of effort, you need to think about like what is it that I'm really looking for from this? Because this took quite a bit of time from me, and yeah, it was pretty much a waste in the end. So that's the, I want to say, the more abstract lesson that I was learning. But nonetheless, I think this was cool. I wanted to show off the TS Fresh package. I thought that was really, really awesome, and I'm definitely going to use that in future. And that this is a cool idea, but I did not pursue it fully. All right, now I want to move on to my final submission, my final model that got me the best score in the competition, and just give you a bit of context as to why I landed up with this model. So I'd done these initial attempts. I tried some other stuff out. I tried out some deep learning stuff, but that didn't go well at all. I didn't want to show that off because, man, that was strenuous and I wasn't getting anywhere. I also don't think I would do it justice explaining the ideas there. I was just basically throwing data at models, so not a great approach and not a lot of value there, I don't feel. So I wanted to take you through my final model, and here I decided to go with a single model to simplify things. So again, we have this problem of biasing in the data, like we don't have a lot of actual signal, there's a whole bunch of zeros, and also like we have 194 different models, or different series, should I say. These things were plaguing me, and eventually I was like, you know what, let's just go with the simplest solution possible. And that turned out to be use a single model on all the different series. So treat all the series as training data for one model rather than 194 different isolated series or 585 different isolated series. Rather use a single model. And the simplest model I could think of was linear regression over here. So I actually use the dots kind of wrapper around linear regression. It lets you use kind of lags quite easily, which I ended up using. Initially, I was actually leaning towards using an XGBoost model or a gradient kind of boosting model, one of those like LightGBM or XGBoost, one of these types of things. But I decided to go with linear regression kind of on a whim because I'd recently made a video on linear regression, so it was like bouncing around in my head. It was also just super fast to train, super fast to try things out with. So I decided to go there, and it turned out to work pretty well. So there was that. So I do my imports over here. The interesting import that we'll get to right at the end is Optuna. I'll talk about that. But really, for the beginning part, I'm using dots, I'm using pandas, DuckDB, NumPy, and a bit of sklearn over here. I don't use these imports at all over here, it seems, matplotlib and seaborn. I can leave these hanging around, I suppose, but I don't actually end up using them in this notebook. But it will. Let's go ahead and run this and get all our imports. All right, with the imports done, I then go ahead and connect to our database. In this case, I'm just doing read only, so pretty standard. I'm also using the devices to drop list over here. I decided to remove these from my training set, and then moving on to modeling and submission. So the first part over here is the pivot and melt move that I had in our one of our previous notebooks, in the feature engineering notebook. So I just did this all in one step. I basically grab the data, the daily hydropower production data. I do the pivot and melt move to make sure all the series are the same length. And the only additional step really here is that I filter my data for everything beyond July 2024. And the reason I do this is simply because that's where we have the most signal. So just as a quick reminder, let's jump to our feature engineering notebook, and let me get to that picture real quick. There we go. So in this picture, from July 2024 onwards, that's where we actually have a lot of signal. It's also closest to where we are going to do our forecasting. So my naive move, or somewhat kind of, I want to say, naive move, is that I chopped off the data at this point. So like filtered the data over there and ignored the rest. Now, I don't think that's the best move. I think the winner actually had a way better solution to this, and we'll go through that. But yeah, my move was basically chop off all the data here, ignore all this signal, and just use everything from July onward. And that's what I'm doing here with this filter step. The code before is just the kind of pivot, unpivot move to make sure my series have the same length. All right, so running that, I end up with our data frame. All of the time series have the same length. They're all stacked on top of one another. And just to get a shape or an idea of shape over here, this has about 35,000 data points, closer to 36,000 data points in it. Over here, I extract the consumer device and data user. This is the typical regex move that we've seen before. I cast these as integers as well. I don't actually end up using these, so this is kind of a pointless step, but hey, oh well. So I end up with the consumer device and data user columns as well. Then I go ahead and grab our features from the daily features table that we created in the feature engineering notebook. Now, this was part of my attempt over here. I'm not going to go through this. I wanted to use these this consumer device and data user kind of features. These are static features, or these are static covariates in kind of Dart's language. These don't end up helping me, so I left this code here because I initially tried things out using the static covariates, specifying static calls, but I don't end up using it, so I'm just going to skip this for now. If you do want to explore that, you can uncomment this code and try it out, but yeah, I didn't get much luck with them, so I'm going to ignore that. Now, here's the main kind of part of my training data setup. Basically, I create an empty dictionary over here. And in this dictionary, I want to store all the data that's relevant for each of my series. By that, I mean the first thing that I do over here, or in this loop over here, is that I iterate through all the different series. So going through each series name, so the kind of consumer device data user combinations. And what I try to do, so I wrap this in a try except block. What I try to do is first convert the data for that specific series, so extracting each series and convert it into a Dart's time series. So this is series TS, or series time series. Weird variable name, but yep, that's what I went with. So convert this into a time series, and then I scale it. So over here, I'm actually using this scaler, which is a wrapper in the Darts package that you can wrap around an scikit-learn scaler, or you can write your own and use it on top of a time series. The reason I'm scaling the different features is because I am using linear regression, and it seemed to perform better when I used scaled variables rather than kind of the plain old variables. Now, if I'd gone down the gradient boosting side of things, you don't need to worry about scaling because gradient boosters typically use decision trees, and decision trees don't care about scale. But since I'm using a linear regressor, this influences it quite a bit. So I apply a scaler. Then I get the scaled series, so I apply the scaler to my time series. I split the data into a training set and testing set. Pretty typical kind of split, or similar to what I was doing in the isolated series attempt, reserving 31 values, which is our forecast horizon, reserving 31 values as our testing set. I then apply the scaler to my training set. So I need a separate scaler for the training data, and this is because I want to avoid data leakage. What I mean by that is if I had used this scaler where I have scaled the full series on my training set, this scaler has knowledge about the future according or relative to my training set, right? It has scaled the full data set, so it knows about these 31 values that I have reserved for my testing set. So to avoid data leakage, I actually need to create another scaler that does not have context over my testing time series. So I need a completely separate scaler that I use over here, and I apply that to my training set. I then store all of the values that I've just generated in my dictionary. So my dictionary's key is the series name, and then I have these values of the time series, which is, you know, the full time series, the scaled time series, the actual scaler that I used on my full time series, the training set, the training scaler. All of this kind of information I store in this dictionary. So I'm basically going series by series, applying scalings, doing the train test split, applying scaling to my training data, and storing all of that information in a dictionary so I can pull it easily as and when I need it. Let's go ahead and run this and generate our TS, or time series dictionary over here. Right, with the TS dict set up, I then go and create lists of my time series, the full time series and the training time series. So over here, I'm just extracting my scaled training set over here from the dictionary into a list, because in Darts, you can pass a list of time series for your model to train on rather than kind of doing it one by one. So I don't need to loop again. I can just pass it a list of information and it will train across that entire set of time series rather than me calling fit each and every time that I need it. So I do this for the training set and the full set because I'm going to use the training set to kind of evaluate different model combinations, and I'm going to use the full set to actually produce our forecast. Then I convert our features to a time series type in dots because I'm actually going to use these as covariates or features in my time series model over here. So I use the from data frame on the features df and specify the time column as the kind of date column that we have. I apply scaling to the features as well. So I'm using a standard scaler on here. And yeah, just apply that across the different features. So these are now scaled. I then read our sample submission, extract the date and source from it as a data frame. So what we've seen before. I then write a couple of utility functions over here. So this function over here is a scoring function, which will take in the model, my time series dictionary, the sample submission, any future covariates. We'll touch on that in a bit. The forecast horizon and whether or not I have applied scaling over here. So what this will do is loop through my different series, and specifically when I do a score, I only wanted to score on the time series that I actually am going to forecast for. That gives me a more accurate score. I felt that it would give me a more accurate score. So I loop through them, create predictions, and in dots, I need to specify which series I'm forecasting for. So I have to give it the series that I'm forecasting for in each case. So as I loop through, I need to specify the time series that I'm forecasting for with the model. I create the predictions, and then I undo the scaling that I did. So when I create my forecast, I don't want my forecast to be scaled. I need it to be in the original units, which is why I stored the scalar in the first place so that I could undo the scaling. And I do this via an inverse transform over here. So if scaling is applied, go ahead and grab the scalar from my time series dictionary and apply that to the predictions. So unscale them. I then store the root mean square error of that specific series and compare it to the actual values. So I compare my forecast to my test time series, get a root mean square error, I append it to this list over here. And what I return from my score model over here is the average root mean square error across all of my different forecasts, because I believe this is what Zindi was doing, or the competition site was doing. It takes your forecasts and looks at the average root mean square error, and that is your final score. So that's what this guy does. And then I have another utility function over here that produces the prediction. So this will take the full model, and similar idea to the scoring, I'm going to iterate through all the different series that I actually want forecast for. But in this case, I just create predictions. I then convert those predictions to a data frame over here, and I store it in a final data frame. So I concatenate it together. So as I produce a forecast, so I will concatenate them together. I then sort the values and produce an ID and return a data frame of forecast. So this is just doing some formatting basically so that my forecast looks like the sample submission. So a very similar idea over here with the iterations, but in this case, I'm just producing predictions. I'm not going to do the kind of root mean square error scoring because this is for the full set of forecasts. I can't get a root mean square error score because I don't know the future values. I have to hand in my predictions to actually get a score. All right, so let's go ahead and make sure this function's in memory. All right, now we actually get to applying our model. So over here are my model quags, or my model keyword arguments. I stored these in a dictionary because I'm going to use these twice. Once for my testing set, or where I produce a root mean square error score, and the other time for my full model. So I decided to keep these in one dictionary just to keep things cleaner. So over here, I'm specifying a lag of -1. So this means that in my model, I want to use the t-1 value as a feature. That's what this lag means. The output chunk length is how many values to forecast for before reevaluating and creating the next set of forecasting. So you have the sliding window of forecasts happening. I also specify lags for my covariates. So this is a 1 month lag like we had in the analysis notebook. I don't use the static covariates. Like I explained, I didn't really get much luck with them, so these are false. And then specifying a random state so that I get consistent results out. Let's set up our keyword arguments. I then go and set up my model over here. So my linear model is the Darts linear regression model. I then give it my keyword arguments. So the star syntax just means unpack those arguments as keyword arguments in your function. So yeah, kind of some fancy footwork going on here, but it basically means use this stuff as the arguments to the function over here, or this class. I then set up my future covariates, and with Darts, I need my future covariates to be as long, or be a list as long as how many training sets I have. So this is just like a bit of dummy code that basically copies my covariates as many times as there are training time series. So it's just a repeat of all of the different time series over and over and over again. So if I have 50 different time series, this will produce 50 duplicates of the covariates. In this case, I'm only using the precip to snow ratio as my only feature. So the only features that are in my linear regression model are the precip to snow ratio shifted by 30 days. So negative 30 days, a month ago's precip to snow ratio. And the other feature is yesterday's value for kilowatt hours. So those are my only two features, right, that I'm using in this model. So running this with the .fit, specifying my training set and my covariates over here. Future covariates in Darts just means that I know the future values, and I happen to know the weather data in future, which is why I can specify it as a future covariate and use a kind of lag like this. So let's go ahead and run this guy and fit it. With the model setup, I then call my score model utility function to actually get a approximate root mean square error score of how my model is doing. And in this case, it's doing pretty well. It has a root mean square error of 4.91, which is really good, right? I mean, our averages were like 8 or something like that for the other models, so this is a really good score. Now, this isn't the true score that I'll actually get, but it's a good approximation. Since I'm happy with this, I then go ahead and plug in my quarks into a full model. The only difference here is that now I'm going to use my full TS list. So I'm not going to use a training set. I'm instead going to give it all the data that I have. So these are not cut by 31 days or not trimmed by 31 days. I'm going to give it all the data that I can. All right, so we've got our model set up. And then I go ahead and create predictions with our full model over here, calling this utility function. So this produces the forecast for us. And there we go. Our forecasts 31 days into the future and the values that we expect. I just need to basically consume the ID that I've got and the kilowatt hours to create a prediction. So over here, I take the ID, kilowatt hours, select those, convert those to a CSV, and store the result in my submissions folder. I'm also ignoring the index here because I don't want that in my CSV file. I don't want any index values. I just want the ID and the kilowatt hours. All right, and that produces a submission for us. So let me go ahead and plug that into Zindi, and so we can get a score for it. Right, so click on get a score and drag and drop my forecast.csv. I could probably come up with a better name, but that's what it is. So let's get a score. All right, and this gives us a public score of 7.24, but the private score is about 4.55, which means our approximate root mean square error score that we had on our testing set is actually pretty close to the full score that we get. Now, the reason that I jumped so quickly on the leaderboard, or if you didn't see my previous video, I was pretty surprised that I jumped to 4th place from like 50th place, is because the public score was like kind of bad. Like a lot of folks had defeated this number over here, but my my public score wasn't that good, but my private score turned out to be pretty darn close. So that was the cool part, I want to say. All right, so that's what gets us to the optimal submission that I could produce, and this got me 4th place on the leaderboard. Now, I know you might be wondering, well, before I answer the question, let me go ahead and close the connection to DuckDB just for safety. You're probably asking, but wait a second, how did you get those parameters? Like, how the hell did you know to go ahead and use a lag of -1, a chunk length of -9, and a future covariate lag of -30, and not use static covariates and all that? Well, here's the secret source of how I found that. I used the Optuna library to try out a whole bunch of different combinations pretty systematically with these different variables. Now, I'll go through Optuna briefly, but I do have a full video explaining exactly how to use Optuna If you're familiar with grid search in sklearn, it's very similar to that. I just find it a little more pleasant to use than grid search. It's also more efficient in my opinion. But I'll leave a link to my full video about Optuna if you are interested in seeing that, or if you're unfamiliar with it. But to take you through it, in the Optuna framework, you can set up an objective function. So over here, I called this covariate objective. You give it a trial value, so it's going to basically try a whole set of different kind of combinations of parameters. And then when you specify the parameters of interest, like the lags, for example, you don't have to give it a specific value. You can give it a set of values to try. So in this case, I'm saying trial.suggest categorical. So I want you to suggest a lag between these different options. So my intuition was like, use, what a lag of -1. So yesterday's value compared to when you're forecasting, or use -1 and -7. So include a week ago's value, or -1 and -14 to see if 2 weeks ago influences it. I then try different output chunk lengths over here. So between 5 and 20, I suggest values between those two. And then also the covariate lags, try a whole bunch of different covariate lags from 0, so at time t, or -30, or -60, or -90. I then also give it different features to try. So these are the features that I thought were most relevant or would perform quite well. So there's average temperature, average dew point temperature, wind speed, precip to snow ratio, and the day of year. And then if I have all of these, I was like, well, maybe you should try use all of them, not just one of them. So this will then go and suggest using, or different models using each of these in isolation, or use all of them at once. And that's what the selected covariates will do. It will select one combination of these, or like one of these options that I've set out over here. I then go and create my future covariates, set up my model with the suggested values, fit it and score it, and return the mean root mean square error. So in Optuna, your objective function will return a value, and you tell Optuna, hey, the value that you get back, I want you to minimize it or maximize it. In this case, it is the root mean square error, so I want it to be minimized. So all I have to do is, let's run this objective function. I create a study in Optuna and say, hey, with this, I want you to minimize the value that you get back. I then call .optimize with my objective function, and I say try 50 different combinations of this. I gave it n jobs equals 8, which means do 8 jobs at a time in parallel, and show me a progress bar while you're doing this. Now, in the actual competition, this number of trials that I had was way higher. I think I tried it like with 300 or 400 different trials. So what it's going to do is create, or it will create, in this case, 50 different models with different combinations of these parameters, and figure out which gives me the best performance in terms of average root mean square error. So if I go and run this, it's going to go in the background and try all these different combinations of parameters and get me the best model. So if I run this guy, let's just let this go for a while. It's going to go and do all that work for me. All right, and once this is done running, you can see the output gives you different trials. So for example, it will have like trial 7 over here and give you a value of what it finished with. So in this case, trial 7 finished with a value of a root mean square error of about 5.1, 5.2. And if I scroll to the side over here, it tells you which parameters it tried. So in this case, on that first line, it tried -1 and -7 as the lags. The output chunk length is 17. The future covariate lags are -60. The future covariates that it used was the precip to snow ratio. And the current best trial is trial 7. Well, that was the only trial at this point with this score. So it basically has gone and tried 50 different combinations of parameters from my suggested set of parameters and produced the root mean square error scores. So this is an automated way to search your parameter space and give you the best results. So let me close that. The convenient thing to do, though, is to take your study that we just created and get the best parameters. So this will give me the parameters which gave the lowest root mean square error score. So over here, it turns out that it gave me a lag of -1, an output chunk length of 7, and then the future covariate lags was -90, and it just used average temperature. Now, this is different to what I actually used because in the actual competition, like I said, I tried a lot more iterations. So I didn't just use 50 trials, I used like 300 or so. And I did not just submit the best parameters, I got the top 10 parameters, I believe it was, and I tried all of those to see which would give me the best score on the validation set. So yeah, that is how I found or wound up with these parameters up here. Yeah, so I just wanted to explain that because I kind of glanced or gleaned over it and kind of said, yeah, well, I just used these. I found these by searching a whole bunch of different combinations and trying out a bunch of different combinations. All right, and that explains my process and how I got to where I got to. But the last thing I wanted to touch on, just at a super high level, was the winner's solution. So after the competition, I was very interested in what everyone else was doing. Like, oh man, now that the competition's over, like everyone can reveal what they did. And I think like most of the top 10 of the competition leaderboard like released their results. So on Zindi, you can actually find in the chat section, you can find links to their notebooks if you're interested in seeing what everyone tried. Obviously, there's my solution, just saying, we went through. And I wanted to go through a few of them, but I decided to just reach out to the winner, Data Style Bender on Zindi, and ask if I could review their solution. Now, as I say, I'm just going to go through their solution at a high level. There is a lot going on, but I just wanted to extract what I thought was really valuable from reading through their solution. All right, so opening up the winner's solution notebook that I have in my repo here, the first thing that I'm noting, like just full transparency here, this is a copy of the winner's work. So all credit for the code and ideas should go to them, not me. This is not my code. I do leave a couple of notes in this version of the notebook. I have kind of I want to say, torn it a bit, Frankensteined it a little bit. So running this in my repo might be a bit of a challenge. But if you are interested, please go to their repo, go and check out their repository of the winning solution, give it a star, fork the repo, show them all the love because they deserve it. So I just wanted to note explicitly here, this is not my work. Okay, now going through this, I'm, like I said, just going to go through this at a high level. So what I wanted to note from this notebook is that the main model that they're using is a gradient boosting model, a light GBM model. And interestingly, throughout, what is used is more kind of traditional machine learning. So they are not using darts, they are not using any lags or anything like that. They are treating this as a pure kind of regression type problem and not using any of the kind of fancy footwork or anything like that, which makes it also like super impressive that this is being treated as a traditional regression problem. The lags and stuff like that is not being used at all. So one of the first things that I want to note, or that I will take as a lesson learned from this notebook, is that the winner treated the training setup quite interestingly. They basically split up the data into 4 discrete kind of sets. The first set of data was August to September 2024 and October 2023. So this very like dense signal. If you actually look at the plots, that's where most of the signal is. They also have this kind of like lower signal area in data 2, or like the second set of data. Data 3 is like all the other kind of quiet periods, like these random bits of, I want to say noise, but random bits of signal. And then the fourth set is all of the data. So they've got these 4 different sets of data that they're using. They also have different model configurations. So they used 7 different light GBM models and ensembled them together for one powerful model. So I'll go through that a little bit, but the interesting part is that each of the 7 different light GBM regressors had different objectives. Like one is more precise, the other one is more feature selective, the third one's more robust, etc. And this is explained quite nicely over here. But before I go into this, what I wanted to look at next was the data cleaning that they went through. So an interesting idea here, dealing with that kind of data biasing, so having all that zero signal in between 2 sections of high signal in the time series, this was dealt with really well by the winner. Basically, what they did is took the data and used a sliding window of 1 week to see where there was signal. By that, I mean that they grouped the data by a 7-day sliding window, checked if the data had a sum of 0, so basically there was no power produced for a week or that week sliding window, and if there was no data in that window, they rejected it. But if there was any signal whatsoever, so if 1 day out of the 7 had signal in it, they accepted this as part of the training data and called this an online-offline data separation. Now, why this is advantageous is because it preserves as much data as possible, but rejects as much of the 0 data as possible. So this is a really clever way of dealing with the fact that we have certain sections that do not have a lot of signal in them. So this technique was pretty damn impressive. Like, there's a lot of code over here that deals with it, but I thought it was really cool. So this plot shows you where there were a lot of offline days in the data, or sections of the data considered offline. So this orange line shows us that between January 2024 and July 2024, there's a whole bunch of offline days, and this is going to get rejected, basically taken out of the training set. Whereas these little bits over here, even if there's a tiny bit of signal, this is going to be taken as part of the training set, which maximizes how much training data you have and doesn't do the kind of naive thing that I did, which is basically, hey, chop off and reject all of 2023's data, basically, and all of the 0 data. This was a really great way of preserving as much training data as possible, and obviously produced the best results possible. So that idea was really cool. The next thing that I'll compliment, and is a really good lesson, is their attention to feature engineering. The features that they generated were really impressive as well. Now, they did do the typical kind of feature engineering that kind of we did as well, like, precip to snow ratio, looking at precipitation, all that. But one of the cool parts that I thought is not so much because it helped the model a lot, but just to show you like the ideas they had, was getting all of the holidays in Pakistan. Now, Pakistan is predominantly Islamic, so this is grabbing not just the public holidays in the region, but also looking at holidays like Ramadan and Eid and these kinds of holidays, which I thought was really clever because, maybe power fluctuates a lot when it's Ramadan or a public holiday in Pakistan. So I thought this was really awesome. The other feature that I found impressive was their use of rolling features. So I actually want to find that over here. So they are using a exponential weighted moving average to basically look at the features. So what I mean by that is, in this case, this is temp exponential weighted moving average over 3 days. And what this does is it spans 3 days, right? But an exponential weighting basically means that you weight data closer to where you're forecasting more heavily than data that is farther away. And this makes a lot of sense for a time series problem, because data that is closer to your forecast dates obviously bears more weight than something that happened a year ago. So this is an exponential weighted moving average, not just a plain old moving average. So these kinds of ideas were really cool to see. They also used volatility measures. I had one for wind speed, but the temperature volatility is included here. Yeah, just some really cool ideas here in the feature engineering section. Then just to show off the kind of model setup over here, as I mentioned, there are 7 different light GBM models used here. And the configurations are, as we said, kind of like the precise versus more robust. So this is an ensemble of 7 different models stacked on top of one another, which I thought was a really cool idea. Now, I want to quickly go to the next section where it actually shows the results of these and just explain a bit what this means or what this implies from my perspective. All right, so scrolling down to a section over here where we actually look at the feature importances of these models. This is model 1, data 1, and I'll explain why I'm going to focus in on this in a few. But basically what I wanted to note is that while I think the 7 different models is impressive, like using an ensemble of 7 different models is impressive, the real insight that I got from here is that these volatility measures, or these temperature measures, this volatility measure, this exponential weighted moving average, this extreme temperature feature, all of these clearly show that these features are quite important, right? This is a feature importance plot. But what I extracted from this is that clearly these have non-linear relationships with kilowatt hours. Why I say that is because gradient boosting methods typically thrive on non-linear relationships. Now, I'm pointing this out because I focused on linear relationships. Well, clearly I used linear regression, but this shows that these features have strong non-linear relationships with the output, with the kilowatt hours produced. So while I think the ensemble is great and the model setup is great, I think the real insight that this notebook shows is that there are these nonlinear relationships and can be used as powerful features. So it's not so important that light GBM was used and 7 of them were used, rather that there are these really powerful features. So it's not so much the model, but these features that are strong, in my opinion at least. Now, why I fixated on data 1 and model 1 in this notebook is because in the final prediction, where the author is doing basically a manual ensemble, so they're doing a weighted ensemble here. And if you're unfamiliar with ensembles, this basically means that each set of predictions, so you have 7 different models, or a whole bunch of different models, should I say, the predictions are weighted basically across those model outputs. So each one gets its own weight to kind of declare what the prediction should be. Now, this is a little confusing, I'll say that, because there are all these weights given to each of the different predictions. So you have like ensemble models producing the predictions, but then you are ensembling again across the training set, which is a little confusing. But if I simplify this function, which I kind of did in the background, looking at the weights and the predictions, it turns out that model 1 and predictions 1 get the most weight. These carry like about 87% of the weight. So 87% of your prediction comes from this predictions 1, which is a result of using dataset 1 and using that kind of ensemble of 7 different light GBM models. Now, thinking about that, it basically means that the strongest signals, right, that's what data 1 contains, or that first split contains, the strongest signals bear the most weight, which makes sense, right? Because if you want to minimize your root mean square error, you should really fixate on the signals that are strongest. They're going to contribute the most to your error. So this makes sense. And why I was pointing out the features before is because those were the important features for this predictions 1 over here. So I just wanted to point that out and show that off, because those features are really impressive. They work really well. And I wanted to point them out because if you are thinking of taking up this challenge or doing this challenge, a good starting point is using those features, or using those features in combination with the linear features that I found, and maybe producing a powerful model that way. I just wanted to point those out. But nonetheless, I would say if you are interested, go through this notebook. I think it's got some cool ideas in it. There is a lot of code. And there are like a few confusing steps, but I think you can learn a lot if you're unfamiliar with these kind of like ensemble techniques and that kind of thing. But really, the deepest lessons learned, for me at least, is really fixating on your feature engineering and really fixating on preserving your training set as much as possible. So getting as much training data as possible and really working hard to get as much training data as possible, and specifically as much clean training data as possible. And that finally brings us to the conclusion. I have really enjoyed kind of reviewing all of this work that I did and reviewing this competition and really digging into how I got to where I got to. There's a ton of different lessons that I learned that we went through together in this process of reviewing the different notebooks and reviewing the winner's solution. Again, congratulations to the winner. I think they did a really good job. I'm really impressed by their solution. I hope that this walkthrough has given you some new ideas or new perspectives and different techniques to try out on your next project. Or even if you're looking for a project, why not try out this power prediction project? The data's still there, you can still get a score. And if you do, let me know what you tried in the comments below. I'd love to hear about that. If you did find this video valuable, please do consider subscribing to the channel, liking the video, or joining to become a channel member today. Thank you so much for watching, and I will see you soon.